In this compilation, we will discover and master creative coding one step at a time. We will build 8 visual and interactive projects, each one focused around a different animation technique. Only when you fully understand the code, you can control it and make it do whatever you want. So, as always, we will start from scratch with no frameworks and no libraries, and I will explain every line as I write it. Click the like if you want to learn more about creative coding. Thanks. In the first part, we will build a Constellations effect. It will serve as a shared code base with particle system logic and a simple state manager class. And then we will reuse that same code structure for each project that comes after. That way, I can do the setup just once, and we can use our time to take each experimental variation much further. Let's go! Simple things can be beautiful. This entire effect is based on a rule that says when 2 particles are close enough to each other, connect them with a line. Define a rule, apply that to a blueprint, and create many particle objects using that blueprint. That's how you build a particle system, one of the main pillars of creative coding. This is so-called Constellations effect because it looks like diagrams of star patterns. It was made famous by the Particles.js library, and today I will show you how to make it completely from scratch with JavaScript. No frameworks and no libraries. All you need is a code editor and a web browser. This class is for beginners. A basic knowledge of HTML, CSS and JavaScript is needed to get the maximum value. In index.html, I created a simple generic web page. I linked my CSS style sheet and JavaScript file, and I created HTML5 canvas element with an ID of canvas1. Today we will use fundamental programming principles and techniques, functions, arrays, and for loops, and step by step we will add more and more features to build our effect, while making sure we understand every line of code. I could have used a library, but without full understanding of how the code works, we would always be dependent on that library and its features, and what they do and don't allow us to do. Being able to write and fully understand the code gives us an ability to modify and enhance this effect in many different ways, and we can use it in many different types of projects. In style CSS, I gave canvas a black background. I position it and I define a few basic global reset rules to make sure our web page looks the same in different browsers. I will split the logic in 4 main code blocks. Project setup here. Particle class will contain a blueprint to create individual particle objects. Effect class will be the brain of our code base. It will manage all particles, and animate function will run over and over, updating and redrawing the shapes to create animation. I point JavaScript towards canvas element we created in index.html using getElementById. CTX, shortcut for context, will be that canvas variable .getContext, and I pass it 2D to create an instance of something called canvas rendering context 2D, which is basically a built-in object that contains all properties and methods we will use for drawing today. I take canvas from line 2 again, and I set its width to the full width of the browser window. Canvas height will be the same as the height of the browser window. I will console log CTX, and we can see that canvas rendering context to the object I mentioned before. If I open it, we can see some of its properties. For example, we see that the default fill style is set to black. I can take CTX variable and access this fill style property like this, and I can override it to a different color if I want to. I can also call built-in fill rectangle method. So all canvas properties sit here. If I scroll down and I open this area, I can see all built-in drawing methods. Fill rectangle method is here. I pass it 4 arguments, x and y coordinates of the top left corner of the rectangle, and its width and height. Because I set my fill style to white, we are drawing a white rectangle of this size at these coordinates. I can move it around by adjusting the coordinate values. I always do a small test like this just to check if our canvas was set up correctly and that everything is working. All is good, so I can delete this. Click the like if you're getting any value and you want more creative coding tutorials. The main effect class is the brain of our code base. It will store all our custom settings and helper methods we will need today. The main thing it needs is the width and height of the available canvas area, because we need to make sure we draw our shapes only within the canvas area and not somewhere off screen. It will expect a reference to canvas from line 2 as an argument, and inside we convert it into a class property. I create this.width property, the width of the effect, and it will be equal to the width of canvas. So we are actually pointing to line 4 here. Same for height. Particle class will contain a blueprint to create, draw, and update individual particle objects. We will define what particles look like and how they behave here. I want to keep object-oriented code structure, and I want to do good coding practices to keep our classes modular and as independent of the surrounding code as possible. I want particles to see properties on the main effect class, so every particle will expect a reference pointing to the main effect object, like this. We are not creating copies of the effect here. We are just pointing to that same effect class from multiple places when we create multiple particles a bit later. From that reference pointing to the main effect class, I can access its width property, and I can say that horizontal x-coordinate will be a random number between 0 and effect width. Vertical coordinate will be a random value between 0 and effect height. Particles will be circular, so radius of these circles will be, for example, 15 pixels for now. Draw method will contain some drawing code. It will define what each particle looks like. I want them to look like simple circles. To keep this modular, instead of pulling CTX from line 3 directly into my class, this method will expect context as an argument. To draw a circle on canvas, we start by calling beginPath to tell JavaScript we want to start drawing a new shape. Built-in arc method, and we pass it x and y coordinates of the center point of the circle, its radius, start angle of 0 radians, and end angle of math.pi times 2 to give us a full circular arc. Arc method just defines a path, it doesn't actually render anything. To render our path on canvas, we can either fill it with color, or we can just outline it with stroke method. I call fill to draw the circle. Particles will be stored here on the main effect class in an array. This.particles will first start as an empty array. Number of particles will be, for example, 20 to start with. I define a helper method here called createParticles. This method will run just once to initialize the effect and create 20 particle objects. Inside, I create a for loop. It will run 20 times. Every time it runs, it takes this.particles array from line 27 and it will call built-in push array method on it. Push method takes whatever we pass to it and it pushes that to the end of the array. I pass it new particle, like this. The new keyword is a special command in JavaScript. It will look for a class with the name particle and it will trigger its constructor method to create one instance of that class. On line 9, I can see that particle class constructor expects effect as an argument, a reference to this entire effect class, because we want to have access to all these properties and methods that sit on the main effect object from inside particle objects. Because here we are inside that effect class, I just pass it this keyword, which in this area refers to the entire effect object. So as we just said, when the new keyword is called, class constructor is triggered, and the code inside is executed line by line to create one new object. We can actually put any code in here. I want 20 particles to be automatically created when I create an instance of effect class, when this constructor method runs. So I say this.createParticles in here, triggering this method. We will need another helper method to handle all particles. I take this.particles array from line 27, which now contains 20 particle objects, and I call built-in array for each method. For each method executes a provided function once for each array element. We need to assign each array element a variable name, so I will call them particle. And for each particle object in particles array, I want to call its associated draw method from line 15. I can see that it expects context as an argument to specify which canvas we want to draw on, so I pass it context like this. And this value will be coming from here, because handle particles will also expect context. We will finish this in a second. First, I need to create an instance of our main effect class, so a custom variable I call, for example, effect will be equal to new effect. Again, the new keyword will find the associated constructor and it will create one new blank JavaScript object and it will assign it properties based on the blueprint inside. It will execute all the code line by line. For that to happen, I need to pass it canvas as an argument, so I pass it canvas from line 2. Remember that we are doing it this way to keep our classes self-contained and less dependent on their surrounding code, on where they sit in our codebase, on their so-called lexical scope. I console log this effect variable from line 42. In console I can see it has width and height, and because line 29 was automatically triggered when we created an instance of effect class, now it also contains particle array with 20 objects inside. Important thing here is to check one of them and make sure all its properties have values and we don't have any none or undefined here, which would mean we have a problem somewhere in our particle blueprint in the area where these values are calculated. All is good here. So far we know all our code is working. It's good to test your code step by step like this to catch any potential issues in time. Now I can take this effect variable and I call handle particles from it. It expects context as an argument, so I pass it ctx from line 3. I don't see anything on canvas, but if you remember, the default fill style color is black. We have black shapes on a black background. I can define fill style in here and set it to, for example, red. Nice, we are drawing 20 circular red particles. This draw method will run 60 times per second for each of our 20 particle objects. For performance reasons, we want to access and override canvas state as little as possible, so instead of running this line of code over and over so often, since all our particles are the same color at this stage, I can delete this and instead I will define fill style here. This line of code will run just once on the initial page load. It's important to think about these things when structuring our code. Try to change canvas state as little as possible to improve performance of your animation codebases. So this is how you create a basic particle system as an object-oriented codebase. We can create many different effects and animations from this. If you want, you can save a copy of the code at this stage in a different folder and use it for other creative coding experiments in the future. Today we will turn this into animated bouncing balls first and then into beautiful particles constellations effect. Sometimes we can't just declare fill style once. For example, maybe I want each particle to have a different color. In that case, I have to define fill style in here and change this setting every time we are about to draw a new particle. HSL color declaration is probably the most useful way to declare colors if you want to animate them or control them with code in any way. It contains 3 values for hue, saturation and lightness, where hue is a degree on a color wheel. Saturation goes from 0, grayscale, to 100% fully saturated, and lightness at 50% means the color is not affected by light or dark at all. We can easily cycle through the entire color spectrum by increasing hue value from 0 to 360. I can do many different things here. I replace hue with a variable, and I can use this.x here, which means the degree on the color wheel starts from 0 for particles by the left edge of canvas, and it increases as we travel right. I can scale it by half, for example. I increase the number of particles to make it more obvious what's happening. We can scale the value here. We can set a specific value, or I can randomize it. To get the entire color spectrum, we can do a random value between 0 and 360. So this is how I can connect it to the horizontal x coordinate. I can also call stroke here, so we are filling the shape and we are highlighting it. By default, stroke style is black. I can change it like this. I can also change line width like this. I want the particles to be fully visible, not partially hidden behind the edges of canvas. This will be especially important when we make them bounce off the edges in a minute. I need to declare radius first before I can use it for these calculations, because this code is read line by line from top to bottom. So I want the randomized horizontal range to start from here, so this.radius, because we are dealing with the center points of these circles. Now it goes from here, somewhere here. we need to reduce that range by radius from both sides actually. So from here, the random range is width minus radius times 2. It needs to be in brackets to give us the correct range of values. Now, if I refresh the page, you can see that horizontally the circles are fully visible. I do the same thing vertically. We want a range from here to here, so from radius to height minus radius times 2. Now all circles are fully visible. I might need to adjust my screen recording area a bit to really show you. But if you are coding along, you can see yourself that it did it. It will work even when we increase radius to 50 pixels. Or random radius between 0 and 50, between 1 and 41. Circles that are less than 2 pixels will be barely visible anyway. We can animate the particles and make them bounce around. Each particle will have update method, which will run over and over for every animation frame, and it will define particles' motion and behavior. Let's start by just making them all move to the right by 1 pixel per frame. If I call update from down here, it will trigger update just once, so there is no movement. We need to call update and draw over and over to create animation, so I will call handle particles from inside animate loop. We call animate, some code runs, and we call request animation frame, and we pass it animate, the name of its parent method, to create animation loop. Request animation frame will automatically adjust to the screen refresh rate, so for most of us it will run this animation at 60 frames per second. We see these trails, it's old paint. We can delete previous animation frames by clearing the entire canvas between each animation step. Built-in clear rectangle method from coordinates 0, 0 to width and height of canvas. Now we see only the current animation frame. I can also declare the speed as a separate property. Vx, velocity on the horizontal x-axis, is +1, 1 pixel to the right per animation frame. And I increase x by Vx here. We get the same result, but now we can flip it and make them bounce, because I can say if x is more than width, set Vx to its opposite value. If Vx is currently +1, it will give us -1, because +1 times -1 is -1. We can also do it for the opposite side using the same line of code. If x is less than 0, again multiply the current Vx times -1, so particles are moving left, their Vx is -1, they reach the left edge, and -1 times -1 is +1. It will flip the direction again. This is a great line of code because it's so simple and it will make the particles endlessly bounce left and right. Because these are circles, x and y coordinates define their center points, so they only bounce when the center point reaches left and right edge. If I want my particle circles to bounce as soon as the right edge of particle circle touches the edge of canvas area, I have to account for the radius here and here, like this. It will work even when each particle has a different randomized horizontal speed. For example, a random speed between 0 and 4 pixels per frame. Or if we want them to start moving both left and right, I want some of them to have plus, some minus speed, so a random speed between -2 and +2. I do the same for Vy, velocity on the vertical y-axis. If I apply Vy to this .y, combination of randomized positive or negative vertical and horizontal speeds makes particles move in all possible directions to all sides. And we will make them also bounce vertically by copying this line and adjusting it. If this .y is more than height minus radius, so on the bottom, or when this .y is less than 0, when it's on the top, make it bounce by flipping velocity y to its opposite value. And this is how you do bouncing. Again, there are so many things that can be done with this. These are extremely useful code bases that allow us to make thousands of different particle effects. Feel free to save this version of the codebase in a separate folder, so you have a quick basic boilerplate codebase ready for your future creative coding experiments, and you don't always have to write this base code structure again. If you observe one particle and follow it around as it moves, you will notice that its color cycles through the color spectrum based on its current horizontal coordinate, because of the code we wrote on line 19. We can achieve the same effect but have more control over the direction of the colors and over individual color breakpoints if we use built-in create linear gradient method. We can just declare it up here on the first page load. Create linear gradient method expects 4 arguments to define the direction of the gradient. I want it to start from the top left corner, coordinates 0, 0, and I want it to end at the bottom right corner, coordinates canvas width and canvas height. The gradient will be drawn along a line connecting these 2 points. I take that custom gradient variable and I call built-in addColorStop method. It expects 2 arguments, offset and color. Offset is 0 at the beginning of the gradient, offset 1 is the end of the gradient. I want 3 breakpoints. We start at offset 0 with white, 0.5 in the middle will be magenta, and end will be blue. I delete this fill style declaration and instead I assign fill style to this gradient variable we just created. As you can see, we go from coordinates 0, 0, top left corner, starting from white, through magenta in the middle, all the way to blue in the bottom right corner, where the gradient ends. Nice! There is also create radial gradient method, in case you want gradients in circles. I can change the size of my particles by changing the radius value. I can slow them down. Maybe a random speed between -0.5 and +0.5 pixels per animation frame. This concludes the beginner version of this class. Now we will take it to the next level and we will use a few common and extremely useful creative coding techniques to turn this bouncing balls effect into the famous particles constellations effect. Only we will not be using libraries. We wrote this codebase line by line and we will fully understand it, which means we can do with it anything we want. For example, I have another class where I made the particles fill letter shapes as we dynamically type that text into an input field. But that's a bit more advanced class compared to this one. Let's cover the basics to make sure we understand exactly how this effect works. Constellations effect connects particles that are close enough to each other with lines. Let's start with that. I create a custom method I call, for example, connect particles. We only want to connect particles that are 100 pixels apart or less from each other. Max distance is 100 pixels. I want to cycle over the entire particles array over all the elements one by one, so we create a for loop. This bit is important. I want to compare every particle inside this .particles array from line 43 against every other particle object in that same array, so that I can calculate their distance and check if they are less than 100 pixels apart. To do that, I need to use nested for loops, a loop inside of another loop. Basically, I want to cycle over the entire particles array, and for each of those particles, I will run over the same array again to compare each particle against all other particles in that array. I don't actually have to cycle from 0 here in the inner for loop, because some pairs of particles will have already been compared in the previous runs of these loops. So the inner index I called B will start from index A, and it will continue from there. It will not start all the way from the beginning, from index 0, because that would mean we are comparing pairs of particles we already compared. Don't worry if you can't visualize that. It will make more sense if you use this technique more often. All you need to understand here is that structuring 2 nested for loops in this way allows me to compare each particle object in this .particles array against all other particles in that same array. We are always comparing 2 particles at the time until we compared all of them, until we covered all particle pairs. We will always be comparing particle object with index A in the array against another particle object with index B in the same array. For each loop, we have to do the following. We have 2 objects, particle A and particle B, 2 points in a 2D space somewhere on canvas. We want to calculate the distance between these 2 points. Let's say particle A is here and particle B is here. We want to know the distance between them. So how to calculate the distance between 2 points in a 2D space? This is a very important coding technique if you want to write code for physics simulations, games, or creative coding projects. To get this distance value, we need to imagine there is a right triangle in between them. This will work regardless of where, in which position relative to each other, particle A and particle B are. We calculate dx, the distance between particle A and particle B on the horizontal x-axis. We calculate dy, the distance between particle A and particle B on the vertical y-axis. We have this side of the triangle. We also know this side. And we know this is a right angle, 90 degrees. Knowing all of this, we can use Pythagoras theorem formula to calculate hypotenuse, the longest side of the right triangle, which is also the actual distance between these 2 points. We can calculate it using Pythagoras theorem formula, which would be square root of dx squared plus dy squared. And since we are using JavaScript for this codebase, we can also use built-in math.hypotenuse method, which will calculate that value for us as well. We just need to pass it dx and dy, this side and this side, and it will give us hypotenuse, the distance between the 2 points. Understanding this concept is extremely important because it can be used for so many different types of projects. I use it a lot when writing code for my 2D games, for example. We know the distance now, so if distance is less than max distance, if particle A and particle B are closer to each other than 100 pixels, we will draw a line from particle A to particle B, connecting them together. I'm still console-logging my CTX variable, so if I open the browser console and I scroll down here, I can see built-in line2 and move2 methods, which we will now use to connect our particles with lines. Okay, so in this area, we know particles are close together, so we want to draw a line. We start a new path by calling beginPath method. Move2 method will define starting x and y coordinates of the line, so we pass it x and y coordinates of particle A. Line2 method will set the next point along a path if we are drawing a more complex shape, but in this case it will define just the ending coordinates of the line, so I pass it x and y coordinates of particle B. Same as arc method, move2 and line2 methods just set the path. To actually render it on canvas, we have to stroke it or we have to fill that shape with color. We have just a simple line here, so I call built-in stroke method to draw that line. So again, we want to connect particles that are close enough with lines. We compare every particle against every other particle in the same array using nested for loops. We calculate dx and dy, and from that we calculate hypotenuse to give us the distance between particle A and particle B. If distance is less than 100 pixels, we draw a line from particle A to particle B. I call connect particles from inside handle particles method here. We are drawing on canvas inside this method and we are using context here, so connect particles will expect context as an argument. And here I take this context argument and I pass it along. Nice, we are drawing the lines. But as we said before, by default, the stroke style is set to black. I go up here and I set stroke style to white. Perfect. I want the lines to be behind particles. We are drawing everything on the same single canvas element, which means that whatever is drawn first is behind whatever is drawn later. What comes last is drawn on top. I put the lines behind particles by drawing the lines first and particles after. We built Constellations effect with no frameworks and no libraries. Well done if you followed this far. There are many ways to improve this. If you look at the lines, they appear and disappear instantly as particles get in and out of range of each other. I would like the transitions to be more gradual to get a smoother effect. We could, for example, connect opacity of the lines to the distance between the particles. If particles are right on top of each other, lines are fully visible. As the particles get further apart, we gradually reduce opacity of the line until the opacity is 0 and the line becomes fully invisible at the exact same point when particle distance reaches 100 pixels. On canvas, we can declare opacity by defining global alpha property, where 0 is invisible and 1 is fully visible. I want this opacity value to be 1 when particle distance is 0, when particles are close to each other. And I want opacity to be 0 when particles are 100 pixels apart. And of course I want to spread the values in between into this range. When particles are 50 pixels apart, I want opacity to be 0.5. When particles are 20 pixels apart, I want opacity to be 0.8, and so on. I do this by using a formula like this. I want opacity to be the ratio between the current distance and the max distance. So, for example, when the current distance is 50 pixels and max distance is 100, it will always be 100. 50 divided by 100 is 0.5. When the current distance between particle A and particle B is 30 pixels, 30 divided by 100 is 0.3. I hope this makes sense. I also want to flip this. When particles are near, distance is a low value. I want opacity to be closer to 1, to the maximum highest range. When particles are far apart, distance is a high value, close to the maximum 100. At that point, I want opacity to be close to 0, close to its lowest point. I can do that by taking the maximum value. We know that the distance divided by max distance will never be more than 1, because this code block runs only when distance is less than max distance. And when you divide lower number by the higher number, you can never get more than 1. For that reason, I can take maximum possible opacity value of 1 and use it like this. Max value minus the ratio between the current distance and the max distance. We flipped it, and now let's say the current distance is 30 pixels. 30 divided by 100 is 0.3, 1 minus 0.3 is 0.7. When the distance is 30, opacity is 0.7. This might be challenging to visualize for some of us. It's quite advanced actually for beginners, but as with other techniques we used today, it becomes easier if you use it more often. All we need to know here is that I'm using this line of code to convert the current distance between particles to a range between 0 and 1, but I'm flipping it, where high distance value is low opacity and low distance value is high opacity. Now I can use this dynamic opacity value as my global alpha property. Global alpha, same as fill style, stroke style, and other canvas settings, change the state of the entire canvas. Which means that once we declare this value, once we set this canvas setting to a specific value, all shapes drawn after this will get that setting. I only want this particular opacity value to affect this particular line shape, only these few lines of drawing code. So I wrap this code block in built-in save and restore canvas methods. Save method will save all canvas settings. We can make any changes we want in here, and those changes will affect only this shape. Then we call restore and we reset canvas state back to what it was at this point where we called save. In this case, we are returning global alpha back to its default value. And now we have a visual representation of what we just talked about. When particles are close, lines connecting them have higher opacity. As particles move further apart, the lines get gradually more and more invisible until they disappear completely, at the point when particles reach maximum distance. I can remove the stroke on particle circles. It will also improve performance of our code base because stroking all these circles is performance expensive. I set the radius to a random value between 2 and 7 pixels. Now, when the particles are smaller, we can better see that when particles are very close to each other, the lines are drawn at full opacity. They are fully visible. We can also make the particles react to mouse. We can push them around and add some physics to make it more dynamic and interactive. We can also experiment with other movement patterns. Right now, the particles are basically just simple bouncing balls. Join me in the advanced section where we implement all these features and we will play with this code base in many different ways. As with every web development project, by default our codebase is not responsive. If we want to make sure the effect scales up and down to fill all available space when we resize the browser window, we can write that logic ourselves. It's simple. I want to keep object-oriented code structure, so down here on my effect class I create a custom method I call, for example, resize. It will take the new width and height as arguments. I need to update some of these properties on the effect class when the resize event fires. I need to update width and height of the actual canvas element to these new sizes. Then I set width and height properties we have on our effect class to these new updated values. We know that when an instance of a class is created, all the code inside is executed. I will take advantage of that and I will put some extra code in here, some code that I want to run at the point when effect is created. We are already doing that with createParticles method. I also want to add event listener for resize event here. We are inside of a class here, so important thing is to either bind this callback function or I can use ES6 arrow function in here. Using a regular callback function will give us an error if we plan to use this keyword inside this event listener. I want this keyword, when used inside this code block, this event listener, to point to this effect object. ES6 arrow functions were created to simplify function scope, and one of their special features is that they automatically inherit this keyword from the parent scope, which is exactly what we need here. I will console log this auto-generated event object here. Now, when I resize my browser window, event is firing and we can see the object here. Inside, I'm looking for the new updated width and height. I find them in here. So we access it like this: e.target.window.innerWidth. Now, when I resize horizontally, we can see it's updating. I know that our custom resize event expects width and height, so when I call it here, I pass it the new updated width and the new updated height. When I resize the window, I can see that canvas size is changing as well. One thing we have to remember when working with canvas is that resize event resets canvas state to default values, so I have to redeclare fill style in here every time it runs. We are inside of a class, so I want to use context instead, and I guess it will be expected here in a constructor. It will be converted to a class property. Now I use this ctx variable and I pass it to the class constructor here. I actually delete this and I use this.context here. Okay, let's say I want to keep this gradient fill even when we resize. I need to copy this entire code block and I put it here inside the resize method, because when canvas width and height changes, I need to recalculate the direction and the breakpoints of the gradient to make sure it covers the new resized canvas area. I will use this.context here, here, and here. And I pass the new updated canvas width and canvas height to create linear gradient method. I can also use the updated width and height properties. When we make canvas larger, we are given particles more space to spread around. This would be fine, but when I make canvas smaller, the way we make particles bounce off the edges, we are running a risk of trapping some particles outside the canvas area. We can rewrite the movement logic in particle update method and make them seek middle of canvas, I guess. Or even simpler, every time resize method runs, I will run a custom reset method on particle class, which will redistribute them only within the newly available area, making sure that no particles get stuck outside the canvas. I only run this after we resized and updated all properties. For each particle object inside particles array, call their custom reset method we just defined. Now, when we resize canvas, particles always reset to fit into the newly available larger or smaller effect area. Remember that canvas state always resets to default when canvas is resized, which includes fill style and stroke style resetting to the default black color. That's why we have to redeclare our colors inside our custom resize event. I want the particles to react to mouse. I will create a custom mouse object as a property on the main effect class. Initially, I set x and y coordinates of the mouse to 0, 0. We will also keep track of whether mouse button is pressed down or not. We will also have a radius around the mouse, an area around the mouse within which the particles react to it. We can think about it as a mouse influence area. I create another event listener here. I copy it 2 more times. We will listen for mouse move, mouse down, and mouse up events. I put a console log inside mouse move event and I will log that auto-generated event object, just to see what kind of information about the mouse event we can get. As I move mouse over canvas, mouse move event is triggering and mouse event object is being generated. I open it. Here I can see x and y coordinates where the cursor is. Perfect. I want to make sure these mouse coordinates are available all over my codebase, not just inside this callback function on event listener. So I will assign them to x and y properties on my custom mouse object. I can delete this console log. I only want mouse interactions to happen when mouse button is pressed down. Only if pressed property from line 56 is true. I have to use this dot here and here. OK. When mouse down event fires, we set mouse pressed to true. On mouse up, we set it to false. On mouse down, I will also update current x and y coordinates, like this. I console log mouse x and mouse y to see if it works, if these values are being assigned to our custom mouse object correctly. Yes, that works. I will handle mouse interactions inside update method on particle class. I say if this.effect.mouse, this.effect reference is here on line 17, and through that we are accessing mouse object from line 55. Pressed property here on line 58. If that is true, we want to calculate the distance between this particle object and the mouse. Again, we want to calculate the distance between 2 points in a 2D space, this time between particle and mouse. We calculate dx, the distance between the particle and the mouse on the horizontal x-axis, dy, the distance between them on the vertical y-axis. We have 2 sides of an imaginary right triangle. To calculate the distance between these 2 points, we need to know the length of hypotenuse, the longest side of the right triangle, opposite to the right angle. We can use Pythagoras theorem formula, which would be square root of dx squared plus dy squared. Or we can use built-in math.hypotenuse method, since we are in JavaScript environment. When mouse is pressed, we calculate the distance between mouse and particle. If the distance is less than mouse radius, I want to calculate the angle between mouse and particle, so I know which way I want to push the particle. I want to push it away from the mouse, and that could be in any direction, depending where mouse and particle currently sit relative in relation to each other. I calculate that angle between them using math.atan2 method. Notice I have to pass it dy first and dx second. Math.atan2 gives us the counterclockwise angle in radians between positive x-axis and a line projected from point 0, 0 towards specific x and y coordinates. It gives us this angle. The resulting values are laid out differently if you use particle first or mouse first when calculating dx and dy, but it doesn't matter because we can adjust our code to whatever values it's given us. Basically, we use math.atan2 to give us a sense of direction. Whatever the result is, we can work with it to make it do whatever we need it to do. Let me show you. Let's see how it works in this particular code base. So we are getting a range of values between 0 and plus pi, so half circle, and then 0 and minus pi, another half circle. This single angle value that math.atan2 is returning is all we need to be able to push the other object, in this case the particle, in the correct direction away from the mouse. We do that by increasing x by cosine of that angle value and y by sine of that same angle value. Now, when I click somewhere and I hold mouse button down, we are pushing particles away from the mouse in linear speed. Combining sine and cosine and passing the same angle will make the particles move away in a circle like this. Try to swap sine and cosine, use both sine, both cosine. It should hopefully help you understand better how these values affect particle motion. Trigonometry is complicated for beginners, so don't worry about it too much. That speed is consistent because sine and cosine convert any angle value we pass to it in radians into a range between -1 and +1, and when x and y coordinates are increased by that small value for every animation frame, it results in particle moving by that value for every animation frame, step by step. Particles move at the same speed away from the mouse until they reach the radius of the mouse, and at that point, the distance is no longer more than mouse radius value, so they stop moving. We can introduce some physics and make their speed relative to the current distance between particle and mouse. I want them to move fast when close to the mouse and slower as they reach the edge of mouse radius. When they move outside the mouse influence area, they will completely stop. That force is the ratio between maximum distance, so mouse radius, and the current distance. We will apply this a little bit later. Before we do that, notice how when the particles are at the max range, they kinda move around the mouse in circles, sliding along the outer radius of the interaction area. Nice. Now that particles react to mouse, it is possible to push them outside of canvas area, and once we push them all the way outside, they will get stuck there. We want to prevent that. This code block makes particles bounce from the edges of canvas. We need to make some changes to it. Let's comment out all this code. I'm still animating, which I can confirm by holding down mouse button. The particles will still animate and react to that. If I do this, particles will just move off screen. They will not bounce when they hit the edges of canvas anymore. I say if the horizontal position of the particle is less than this dot radius, which means the particle circle is touching the left edge of canvas, make sure it can't go any further left. If it was pushed further left by large force, it doesn't matter because we will set it back to that position exactly on the edge, and we will flip its Vx to the opposite value, making it bounce and making it travel to the right. As you can see, after doing this, we can no longer use mouse to push particles outside of canvas here on the left edge. Let's do the same thing for the right edge. I can use else if here because particles can be both close to the left and the right edge at the same time in the same animation frame. Else if horizontal position is more than width of canvas minus radius of the particle, meaning that the right edge of particle circle is touching the right edge of canvas, we make sure it can't move any further right, and we flip its horizontal speed to its opposite value, making it bounce and move to the left. If I try to push particles on the right edge here, I see they can't be pushed outside of canvas anymore. Nice. I want to do the same thing for top and bottom edge of canvas, so I copy this code block. It will be another else if, this time covering the vertical movement. If y is more than radius, y is equal to radius, and we flip velocity y to make it bounce and move down. If y is touching or is below the bottom edge, we make sure it can't get any lower than that, and we flip vy, making it move back upwards. I tested by trying to push particles outside of canvas on all four edges. I increase the radius. Let's do 300. Be careful with the number of particles. Increasing the number of particles will exponentially increase how performance demanding our codebase is. Same with max distance. If I increase max distance, we are connecting more particles, drawing more lines, and at some point you will notice it starts affecting frame rate. There are many more ways to optimize this codebase and make the animation very smooth even on the oldest computers. I will cover some of those more advanced optimization techniques in a future class. I want to really test that it's impossible to push particles outside of canvas, so I increase mouse influence radius to 350 pixels. I am squeezing them against the edges of canvas, but as you can see, they don't get stuck or pushed outside the boundaries. Perfect. I can set mouse radius back to 150 pixels. I want to change the color of the gradient. I change it down here inside the resize event listener. White, gold, orange, red. And also up here on the first page load. Whenever we make any changes to the gradient, the way I structured this code, we need to always change it in these two places, unless I decide to refactor this later. Particles move away from the mouse in linear, consistent speed. I want particles to have some physics. Here I am calculating force. Currently, it's a ratio between mouse radius, the area around the mouse within which particles react to it, area within which I want particles to be pushed away from the mouse, and the current distance. I can use that force value here and here to actually influence particle motion. But when I try it, I see that it still doesn't do any impressive physics. We will have to refactor this formula a little bit. If I increase mouse radius, I can see particles can't be pushed outside of canvas area. But I don't see any real physics. I want acceleration and I want friction. I set particle radius, the size of all particles, to be 2 pixels up here. I will make particles move very fast when they are close to the mouse. They will get a big push. I want them to move slowly if they are close to the outer radius of mouse influence area. This is one simple way how to implement it. I will name my variables in a way so that it's easy to understand what they do. I will need 2 separate speed values basically. Vx and Vy, horizontal and vertical velocity values, create the bouncing ball motion that flips when particles hit the edges of canvas area. I don't want to be interfering with how that works, so I create a separate set of variables for speed of horizontal push, push x, and vertical push, push y. The force of this push will be determined by how far the particle is from the mouse when we click or when we move the mouse around. Now we have 2 forces influencing particle motion, the bouncing motion from Vx and Vy, and mouse push force from push x and push y properties. I have to adjust my code with this in mind. Instead of updating x and y positions of the particle in here, I will calculate that push force here only, like this. I delete this entire code block, we don't need this anymore. Let's clean up after ourselves. Right now, particles just bounce around because of lines 58 and 59. I want the push force to also have influence on the current particle position, so I include it in this formula, like this. Okay, horizontal push is strong. Let's do vertical. Right, they fly off fast. In the real world, when you push something, there is a force called friction. Friction works in the direction opposite to the direction in which the object is trying to move, and it gradually slows the moving object down. To simulate the force of friction in our simple virtual physics project, I will create it here as a property. It could also be general property on the effect class if I decide that all particles are subject to the same friction force. Placing it here on each particle object individually allows me to give each particle a different friction value. Maybe heavy particles with larger radius have a different friction value than small, light particles. For now, I set friction for all particles to be 0.95. As we push the particles with mouse, I want them to move fast, But for each animation frame, I want the force of that push to diminish until it reaches a value close to 0. At that point, the bounce in motion will be stronger and it will take over because we are including Vx here. I'm taking the force of the push, and for each animation frame, I'm multiplying it times 0.95, basically reducing the push force by 5% for each animation frame. I do the same thing for vertical position. Now we have physics. To make sure I don't push particles outside of canvas, I will actually cut these 2 lines of code and I will paste them up here. As you can see, the order in which we run these checks for each animation frame matters. Radius of the particles will be a random value between 1 and 11 pixels. I wrap it in Math.floor for performance reasons. It's always easier for JavaScript to work with integers in our drawing code, so I always advise to use Math.floor for all speeds and sizes if the effect you are trying to achieve allows it. I click somewhere to push the particles. If you look closely, you will see that particles that were close to the mouse when the click happened get pushed by a much larger force than particles that were closer to the edges of the mouse interaction area. We can tweak how fast the particles slow down by adjusting the friction value. Now I'm saying slow down the push force by 30% per animation frame. I can also slow them down only by 1% per animation loop. Friction number has to be less than 1, because if you keep multiplying the force by a value larger than 1, it will get faster and faster as the animation runs. In that case, I would just push once and particles would keep getting faster and faster endlessly, which is not what we want. I think 0.95 is a sweet spot, but as I said, you can also make friction relative to the radius of each particle for even more realistic effect. I change mouse radius to 200. Try to push them around, adjust friction values, and see how the particles react. We can turn this into many completely different and beautiful animations. If you want to take this even further with me, create a copy of this project folder and all the files at this stage, because I will write code for multiple variations, some simple, some complex. But I will always start each variation from this point. This is the final project, and I will create multiple experimental branches, all starting from here. Let's go. What if I want to apply certain specific properties only to a segment of my particle objects? For example, I want every 12th particle to have double radius, or I want every 4th particle to be connected to the mouse cursor with a semi-transparent line to create the Sunrays effect. This very simple technique allows us to gain even more control over the code base, and it can be used to achieve many unique particle effects. This is a bonus experimental section of Particle Systems Masterclass. You can download the base source code from part 1 and code along with me today. Or, to get the maximum value, you can watch part 1 first to make sure you understand every line of code. It's up to you. The full playlist is linked below. We can create a gradient background with CSS using the linear gradient CSS function. We can define its direction, and if I just pass it 2 colors like this, they will default to this top to bottom alignment, which is exactly what I want. We are also creating gradient on canvas, which is a completely different technique. I just want 2 color breakpoints at 0 and at 1 offset. As you can see, the white to black gradient is affecting the fill of our particles. We can change starting and ending x and y coordinates here to change the angle and direction of the gradient. I want it to go from top to bottom as well, so from coordinates 0, 0 to coordinates 0 and canvas height. I want white and gold. I will assign this gradient color to stroke style as well to color the lines. I can still push particles around. I increase friction force by reducing this value. Yes, I am reducing push force by 20% per animation frame now. I also want to reduce mouse influence radius. 150. I think 120 will be good for this effect. I want to apply specific properties only to certain particles. Let's say I want to do something only for every third particle. How would we implement that? Here inside createParticles method, I have a for loop that runs 300 times. And as this index increases, we are creating 300 particle objects. I can pass this increase in index value as the second argument to particle class constructor. And up here I make sure the constructor expects that index as an argument. And inside I convert it into a class property. So now my particles have indexes from 0 to 300 as we create them one by one. When we have this, we can do so many things. I could, for example, say, do this for every 10th particle. If particle's index is divisible by 10 with 0 remainder, the remainder operator returns the remainder left over when one operand is divided by a second operand. 13 remainder 5 is 3, because 10 is divisible by 5 and the remainder to 13 is 3. 20 remainder 10 is 0, because 20 is divisible by 10 and there is no remainder. So when particle index is 0, 10, 20, 30, 40, 50 and so on, this remainder check will be true. These numbers are divisible by 10 with a remainder of 0, so for every 10th particle, run this if statement code block. This if statement will evaluate the true and the code inside this code block will run. For example, I want every 10th particle to be much larger, to have a radius of 50 pixels. Or maybe I want every 50th particle to have a random radius between 20 and 30 pixels. Every 100th particle to be between 40 and 50 pixels. This technique gives us more control over our code base. I hope it makes sense. So, what if I want every 5th particle to be connected to the current mouse coordinates? If index of this particle is divisible by 5 with 0 remainder, so for particles with index of 0, 5, 10, 15, 20 and so on, we will draw a line from coordinates of this particle to coordinates of mouse stored on the main effect class. And we stroke that line. Nice! Notice that the lines keep updating and moving with mouse and with the attached particles. Interesting. I call this effect Sunrays. On the first page load, we set mouse coordinates to 0, 0, so we get this. What if the initial mouse coordinates are in the middle horizontally? Or maybe they are on the bottom vertically? Or we can put them in the middle to get this on the first page load. I want to reduce the opacity of these lines, so I will set global alpha to 0.4. Now we can see how canvas state works. Because we changed global alpha property, it now affects all shapes drawn on canvas. I want the reduced opacity to only affect the lines connecting particles and mouse. To limit the changes to canvas state to a specific set of draw calls, we can isolate that area by wrapping the code inside built-in save and restore canvas methods. Now, this global alpha property affects only these few lines of code, and it has no effect on other drawing code inside our project. I try global alpha 0.6 maybe. What if I want every second particle to be connected with a line, so particle objects with index 0, 2, 4, 6, 8, 10 and so on? Or maybe only particles with index 0, 50, 100, 150, 200, 250 and 300. How about every 4th particle? So this is how you can apply certain properties or run certain drawing code only for specific particle objects. Can you come up with any other creative ways of how to use this technique? Do you want to see other ways how you can transform and modify this code base? In creative coding and animation, we can implement many different kinds of interactions. Instead of pushing the particles around, we can make them inflate like bubbles, for example. This is a bonus experimental section of Particle Systems Masterclass. I structured the series in a way where we build the basic shared code base once, and from there we take it in many different directions, always starting from the same point. For that reason, you can build the base code with me, or you can download it in the resources section below, and then you can skip around the playlist and do the projects in any order, or only do the projects you like. Have fun! I remove the black background. I remove the white stroke style to make the constellation lines visible against it. Inside the draw method on particle class, I stroke the particle circles to give them black outlines. Nice! Let's try a different color palette. Gradient will be from pink to red to magenta, for example. When I resize the browser window, gradient resets, so I have to change const to let here. I copy this code without the let keyword. I paste it down here inside resize. I make sure I'm reassigning to the existing gradient variable. I don't want to redeclare it, so there will be no let or const here. Now, when I resize, the gradient adjusts and spreads across the new updated width and height of canvas. Perfect. Even better would be to define a gradient variable as this dot property on the main effect class to keep the classes self-contained. For now, this is fine. It will work well like this. I want to turn the particles into bubbles, so let's make them larger, maybe a random value between 8 and 16 pixels radius. I want them to move slower, so maybe a random speed between minus 0.1 and plus 0.1 pixels per animation frame. When they move slower like this, it will allow us to kinda draw shapes by inflating them. Let me show you what I mean. Before we do that, I want each bubble to have a reflection patch. Bubbles are supposed to be shiny. So this is the body of the bubble, and on top of it we draw another circle as the reflection. I give it a white fill style. The reflection needs to be smaller, but relative to the radius of each particle, because we will be making them grow and shrink soon. When I set fill style here, it changes the state of the entire canvas, so everything drawn on canvas now has white fill style. I need to set fill style here for the body of the bubble. I will use my gradient variable here again. Reflection needs to be bigger. I move it to the left by a value relative to their randomized radius. I move it up vertically, again by a relative value. Normally I would pre-calculate these values for performance, but the core of this effect will be inflating these bubbles, so all the values here will be updating often and they need to stay dynamic. I can remove push forces from particle position calculation here and here. I can also remove these class properties, we don't need them here. I can also delete force and all this code inside the if statement. Instead of pushing particles away from the mouse, if the distance between mouse and the particle is less than mouse radius value, if particle is within mouse interaction radius area, we will increase radius of that particle by 2 pixels per animation frame. Now I have to be careful. I don't have any size limits in place, so particles will grow as long as I'm holding down the mouse button. If I just quickly click and release somewhere over canvas, we get this behavior. I need to keep track of minimum and maximum radius of each particle. That value will be relative to each particle's randomized radius value, but it can be pre-calculated and we always want to do that for performance reasons. Min radius will just keep the value of the original radius of the particle. We have to save it as a separate property because this .radius value on line 17 will keep changing as we interact with the effect. Max radius will be relative to the base radius as well. Maybe radius times 2, times 5. I only want the radius of the particle to increase if mouse is pressed, if distance between mouse and the particle is less than mouse radius, and only when the current radius of the particle is less than max radius. Only then we will increase radius of the particle by 2 pixels per animation frame. I also want particles to shrink back to their original size when they are outside mouse interaction area, so I go all the way outside this if statement. Make sure you have 1, 2 closing brackets in between, and then we write if this.radius, radius of the particle, is more than minimum radius of the particle, keep decreasing radius by 0.1 pixels per animation frame. I test it, I click and I drag the mouse over canvas. Particles inflate, I release the mouse button and they start shrinking. Perfect. Maybe a smaller mouse interaction radius would be better. How about 60 pixels? Yes, I like this. It's your choice, but for this effect I will completely disable lines connecting the particles, since the particles are covering these lines up in most cases anyway. It will improve performance of the effect as well, so I could actually instead add more bubbles to the effect. Be careful with these values. Number of particles will have a big influence on performance, so you can experiment and see what value works well for you. Because particles move relatively slow, I can draw very simple shapes now by inflating bubbles like this. I think this is really cool. You could also make the bubbles or their reflection patches semi-transparent, either by using Canvas Global Alpha property to set opacity, or by setting fill style to RGBA color declaration, where we include alpha as the last argument. You could, for example, also make the particles invisible and very small, and they only appear when we inflate them, creating an interesting mouse trail effect. Also, the motion can be automated. You could, for example, have automated circular motion that inflates particles without the need to interact with the mouse. If you don't know what I mean or how to implement automated motion like that, keep watching the series. I will apply it to a completely different effect, but it can be easily copied and pasted and used here. It's actually much easier than you might think. If you want more creative coding experiments, I'll see you in the next one. Instead of drawing particles as circle shapes with code, we can use a sprite sheet to make each particle one of the randomized star images. Right now our particles look like circles and we draw these shapes over and over using built-in Canvas arc method. Instead of computer-generated shapes, I want each particle to be represented by one of the stars from this sprite sheet. Sprite sheet is basically a collection of multiple animation frames combined into one image. We will assign each particle one of these stars randomly as we create them. You can download the sprite sheet in the resources section below. I put it inside my project folder and I reference it here in index.html. Image source is stars_sprite.png and ID is stars_sprite. Canvas is full screen and the image is behind, so we can't really see it, but I will still hide it with CSS using its ID here. We want to draw that image on canvas using JavaScript. This is a bonus experimental section of Particle Systems Masterclass. I structured this series in a way where we build the basic shared code base once, and from there we take it in many different directions, always starting from the same point. For that reason, you can just build the base code with me or download it in the resources section below, and then you can skip around the playlist and do the projects in any order, or only do the projects you like. Have fun! Up here on my particle class, I create a property I call this.image, and I point JavaScript towards that new image we just imported. I use its ID here to do that. Whenever we are using images in our JavaScript projects, we need to make sure that all the code runs only after the image has fully loaded. When you run this code on your local computer, it will load instantly, but if you decide to put it somewhere online, load event listener is very important. The load event is fired after the whole page has loaded, including all dependent resources such as style sheets, scripts, and images. Now I need to cut all this code. Particle class can be declared outside the load event listener because it will just be sitting here waiting as long as we make sure we only call it after the load from the code inside the load event listener. Inside the load event listener, after canvas element, image element, and all other things on our website are fully loaded and available, only then we will set our project up using all this code here. Let's clean up. I don't need this. We don't need gradient for this effect. I can delete it. We set canvas up, we create an instance of effect class, and we create animation loop. I don't need this gradient, so I delete it. Fill style defaults to black. I can comment out this fill call and only stroke the particles like this. Stroke means outlining them. Now I can call built-in draw image method, which expects at least 3 arguments: the image we want to draw and x and y coordinates where to draw it. I changed the number of particles to maybe 10 so we can better see what's going on. You can see that we are drawing the entire sprite sheet with all 9 frames, and it moves around attached to the particle as it bounces around canvas. We need a property that will represent the width of a single frame in the sprite sheet. The entire sprite sheet is 150 pixels wide, and we have 3 columns of stars there, so a single frame is 50 pixels wide. Sprite height. The height of a single frame is the height of the entire sprite sheet divided by the number of rows. Each star in our sprite sheet is 50 times 50 pixels. We will use sprite width and sprite height to crop individual stars from the sprite sheet. We will also need width and height as separate properties because maybe we want to scale and randomize the sizes of the stars as we draw them on canvas. For now, I will set width and height to 50-50 as well. We will cover scaling in a minute. The second version of draw image method can take optional 4th and 5th arguments for width and height. And if we do that, the entire sprite sheet will be stretched or squeezed to fit that area we define by these values. Right now, we are squeezing all 9 frames into an area of 1 frame. We are squeezing sprite sheet that's 150 times 150 pixels into an area of 50 times 50 pixels. We don't really want to do that. We want to crop out a single frame, one of the random stars, and assign each particle one of the 9 available star images from the sprite sheet. To do that, I will have to use the longest version of draw image method that expects 9 arguments. This will give us the most control over the image because we can have a dynamic cropping area. Let me show you how that works. We pass draw image method the image we want to draw. Source x, source y, source width, and source height. These 4 arguments define a rectangular area we want to crop out from somewhere within the sprite sheet. And we also pass it 4 more arguments: destination x, destination y, destination width, and destination height. And these last 4 arguments define a rectangular area somewhere on canvas where we want to draw that cropped out piece of image onto. So let's say I want to crop out this star. I will set cropping coordinates from 0, 0 to 50, 50, which are the values we gave to sprite width and sprite height properties here. Okay, so now we are taking the entire sprite sheet. We are setting a cropping area and we are drawing that cropped out area on canvas. We know that each frame is 50 times 50 pixels, so if I move the cropping area horizontally by 50 pixels, we get this star. 100 pixels will give us this one. Source Y argument will handle vertical navigation around the sprite sheet. 50 will give us this one. 100 will give us this one. The combination of source X and source Y arguments allows us to travel around the sprite sheet and crop out individual stars. I hope it makes sense. We will talk more about this in a minute. Particles are circles. Images drawn on canvas are rectangles. On HTML canvas, X and Y coordinates of a shape define the middle, the center point of a circle, and the circle is drawn around it, around that center point. With images and rectangles on canvas, the X and Y coordinates define its top left corner. So to align rectangular images exactly over circular particles, we need to offset X and Y coordinates of the image. As we said before, the last 4 arguments we pass to draw image method define where on canvas we draw that image. So I set destination X to the X coordinate of the circular particle minus half of the width of the rectangular image, aligning them horizontally. Then here, inside destination Y argument, I set vertical position of the image to the center point of the particle minus half of the height of the image. Now, the star images are perfectly aligned over the original particle circles. That means we don't need to draw the particle circles anymore. I can delete this code. Little optimization trick here. Instead of calculating this.width times 0.5, 60 times per second for each particle object, we can actually pre-calculate that value just once. It's a simple operation, so it doesn't take JavaScript that much work to calculate this.width times 0.5, but it needs to be calculated thousands and thousands times per second, so if we have more particles, the difference might become noticeable. It's good to always think about how often are your calculations running and pre-calculate some values if possible, so that JavaScript doesn't have to do this extra work. We only make JavaScript calculate that value once when we create each particle, and then reuse that pre-calculated existing value. This will save us some performance. Learning tricks like this is important because they add up and they allow us to have more particles animating on the screen at the same time while still keeping smooth 60 FPS, fluid fast animation. I call that property half width, and it's the width of the particle times 0.5. Then we replace that calculation that happens 60 times per second for each individual particle with that pre-calculated value. We do the same thing for half height. I separated sprite width and width properties into two separate values. Sprite width is the width of a single frame in the sprite sheet, the size of the cropping area. And the width of the particle is the width at which we want to draw it on canvas. Since these properties are two separate values like this, we can scale the star-shaped particles up and down. Let me show you how to do that. We need to make sure we multiply both width and height by the same modifier value, otherwise the shape will be distorted. That distortion might work if you are going for some kind of fake 3D effect, when you want to pretend like we are viewing the particles sideways in a 3D space, but we will not do that today. I will put that size modifier into its own separate variable, and we use it in both places here and here, making sure both width and height are multiplied by the same modifier value. Now you can put different values here on line 15 and see how the particles scale up and down. Anything between 0 and 1 will scale the particle down, anything more than 1 will scale the particles up. This works really well, so we can take it one step further and set the size modifier to a random value between, let's say, 0.2 and 1.2, for example, or 0.9 and 1.9. You can use your own range. I will go with this for now. Source X argument passed to draw image method defines the start of the horizontal cropping area. So if I jump around by the width of a single frame, by sprite width, we can swap the stars around. 0 times sprite width is this one. 1 times sprite width will start the cropping area from horizontal position 50, giving us this image. 2 times sprite width is this one. We can put this multiplier value into a separate property. I call it frame X. I set it to 0 and I use it here. Frames 1, 2. Source Y argument passed to draw image method will handle vertical sprite navigation. It defines where the cropping area starts from vertically. Frame Y 0, 1, 2. Combination of frame X and frame Y can now give us any of these 9 random star shapes, so let's assign each particle a random star. We need to use integers, numbers without decimal points, so I wrap this in math.floor, meaning that frame X can be either column 0 or 1 or 2, and frame Y can be either row 0 or 1 or 2 as well. I increase the number of particles, and we can clearly see that each particle has been assigned one of 9 available stars from the sprite sheet, and also each one has a different size modifier value. Particles still interact with the mouse if we click and drag the mouse around. And the force of the interaction can be adjusted here on line 11 using this .friction property. If I set it to something like 0.4, which is relatively high friction, the lower the number, the higher the friction, by the way. And then I set mouse radius to, let's say, 300 pixels, we get this interesting effect where the stars react slower, kind of like they flow in a thick liquid or something. You can play with all the values we learned about today, and do your own creative coding experiments. How about radically transforming this effect by simply just swapping the sprite sheet into something else, like this? Have fun. There are multiple ways to create liquid effects on canvas. I usually prefer to use the simplest way possible by applying CSS filter property to the canvas element itself. The problem is that when I do that, it applies to everything drawn on canvas, and if you have any fine details in your effect, like in this case we have these sharp, thin lines connecting the particles, applying a filter would make the lines practically invisible. What if I want to liquefy the particles and keep the lines intact? It's actually very easy because we can layer multiple canvas elements on top of each other and choose what gets drawn on which one. This is a bonus experimental section of Particle Systems Masterclass. I structured the series in a way where we build the basic shared code base once, and from there we take it in many different directions, always starting from that same point. For that reason, you can just build the base code with me or download it in the resources section below, and then you can skip around the playlist and do the projects in any order, or only do the projects you like. If you want to build this project from scratch with me, follow the steps in the video description. Have fun! CSS filter property is a powerful tool that we can use to achieve many different kinds of effects. If I apply blur, the entire canvas gets blurry as expected. It becomes more interesting if we chain multiple filters. For example, I can sharpen the blurred shape using contrast and we will get a sticky liquid effect. Notice that the canvas has a background color defined. It's important here for the liquid effect to work. First of all, I will get rid of the white edges around the canvas by setting body background to black. Notice that the lines connecting the particles are now completely gone. They are too thin, so when we blur and sharpen them, they disappear. Even some smaller particles probably disappeared for us. This effect needs big, bulky shapes. I make the particles larger. The filter effect gets a bit weird when particles are too close to the edges of canvas, so I will create some padding to prevent the particles to travel all the way from edge to edge. I want that value to be relative to particle radius, and to save us some performance, I will pre-calculate that value once and I will reuse it, rather than make JavaScript calculate it over and over for each particle 60 times per second. Buffer will be, let's say, radius of the particle times 4. Then I apply it in the code block that handles bouncing from the edges here, 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 here and here. In 8 places, I replace this.radius with this.buffer. Now we have some space between particles and the edges of canvas area. The liquid filter works with some colors, but to get the best effect, we need the highest possible contrast. I will actually remove the gradient and I will set fill style to white. White particles against the black canvas background. If you are not getting the same result, make sure you put background color on your canvas element in CSS. In the resize method, I also have to set fill style to white and remove the gradient code. When I resize, it works great. When I remove the filter, you can see we have just normal circular particles connected with thin semi-transparent lines. Applying the filter will blur and sharpen the particles. It will liquefy them, and it will make the lines connecting them invisible. They are too thin to survive being blurred and sharpened like this. What if I want liquid particles, but I also want to keep the sharp, thin lines? It's easy. We can just use a second canvas element. We need that second canvas in this case because CSS filter will always apply to the entire canvas element. It's not possible to use it to target only specific shapes. Now we have 2 canvas elements, canvas with an ID of canvas 1 and another one with an ID of canvas 2. I want both canvas elements to be positioned on top of each other, so I use general canvas selector to target both of them and set them to the same absolute position on my web page. Only the canvas with an ID of canvas 1 will have a black background and CSS filter applied. There is another way to liquefy particles without the need of having background color on canvas element, which might be necessary if you're doing some type of layering. The way we do that would be with an inline SVG filter. Ask me about that in the comments if you want to know more. Now I can just copy this code block to bring that second canvas into our JavaScript codebase. Variable I call canvas2, and I point it towards the element using its ID, as usual. ctx2 context2 is canvas2.getContext2d. We also make canvas2 full screen by setting its width and height. So now, when I want to draw on canvas1, I use ctx. If I want to draw on canvas2, I use ctx2. I pass handleParticles method both ctx and ctx2 as arguments. Here we make sure those values are expected, and we will give them variable names, context and context2. I want the lines to be drawn on canvas 2, the second canvas that doesn't have a liquid filter applied to it. So I pass connectParticles method context2 to specify which canvas we want to draw on. We need to make sure we clear old paint on canvas 2 between every animation frame, using built-in clear rectangle method. Okay, I can say I'm done because this is already super cool. Look at that. It looks like the lines are oil in water repelling the black liquid around it. This is what I call creative coding. I didn't know it was gonna look like that. I hope you're getting some value today. Click the like if you do. We can make the particles react to mouse in a different way. For example, if I swap distance and mouse radius here like this, let's see. Interesting. And now I invert horizontal push force. Suddenly, when I click the mouse button, we are sucking the particles towards it from left and right on the horizontal x-axis. This is fun to click and play with. Nice. All right, let's do the same for the vertical y-axis as well. Now it looks like we are creating a gravity point, and when we click the mouse, particles become attracted to it and they start moving towards it. We are also getting this nice light bounce back and forth because of the physics we applied earlier. We can adjust the friction value, which will affect the elasticity and overall force of the movement. You can apply different values and combinations here if you want to experiment with motion and interactivity. Okay, this fill style and stroke style is on CTX, so it belongs to this canvas. And we will also declare stroke style for context 2, like this. I set it to white. I can also set line width to 2 pixels. Drawing the effect on 2 separate canvas elements allows us to combine different features. In this case, we were able to liquefy the particles, but still keep the fine, sharp lines that connect them intact. Can you come up with any other use cases for this technique? If you want more particle effects, you might like these tutorials. With each class, we are learning more and more tips and tricks. Try to combine them in different ways if you want. You might come up with something new and unique. I hope you have fun with your creative coding experiments. Click the like if you found some value. How to combine particle systems with other HTML elements on the website and make them interact together. Let's draw particles that fall down across the screen and bounce when they hit a predefined HTML element. It will work with any element we want, or even with multiple ones. In this case, I will make them bounce from HTML heading defined by a h1 tag. This is a bonus experimental section of Particle Systems Masterclass. You can download the base source code from part 1 in the resources section below and code along with me today, or if you want to understand every line of code, watch me write it and explain it from scratch. The full playlist is linked below. Click the like if you find some value. We have interactive animated particles that react to the mouse. They are drawn on HTML canvas element with an ID of canvas1. I want to create another HTML element, for example a h1 tag that says welcome and ID will be caption. The canvas is positioned absolutely, covering the entire web page. I will set h1 to white color, font size 80 pixels, and because canvas is position absolute, one way to move h1 in front of it would be to also give it position absolute, like this. This is just simple CSS. We are positioning 2 HTML elements in relation to each other, in this case canvas element and h1 element. If you follow JavaScript animation classes like this, I assume you are pretty good at CSS and you can use your own CSS code to position the elements wherever you need them to be. I will focus on JavaScript in this class. I will give it a font family impact to make it big and thick. And I use absolute position trick to center the text exactly in the middle of my web page. I also give it border, top, 5 pixels solid white. Everything on the web is a rectangle. Particles will be falling and bouncing from this border. Let's change the gradient to a different set of colors. And maybe I can make it point directly down like this. I copy this code block because resizing resets the colors. I paste it here inside the custom resize event. Now it keeps my new colors when I resize the browser window. I set the initial vertical velocity to 0. I create a new property called gravity. Let's set it to a very small number relative to the radius. Later, when the effect is working, we will change values of gravity to see how it affects particle motion. Radius of particles will be a random value between 3 and 10 pixels. I remove mouse push forces, and I will also remove this entire code block that's handling mouse interactivity. We don't need it for this effect. I adjust this code since there is no push force anymore. For every animation frame, I will increase velocity y by gravity value, which means as the animation runs, Vy is accumulating more and more and the value is growing, and we are then adding that growing value to particles' vertical y coordinate. This will make particles fall faster and faster the longer they fall. They bounce when they hit the edge of canvas. I remove all this code that handles bouncing of the edges except for this check that handles the bottom boundary. Every time they bounce, we swap their vertical velocity to the opposite, but only to 60% of the force, which will make them bounce less and less until they stop. This is nice for some effects and games that include physics if you want particles to bounce for a while and then settle down. I set the initial vertical y coordinate to 0, the top of canvas. I have to do the same inside particle reset method. When particles reach the bottom of canvas, I want the reset method to run, which will move them back to the top and they can fall again. Interesting. Radius is always an integer, and gravity is relative to radius, so they separate into groups like this. Also, Vy is endlessly increasing by gravity, making them fall faster and faster, even when they reset. Every time they reset, I will set Vy back to 0, and I will randomize starting vertical position. I want them to start and reset vertically somewhere between minus radius of the particle and minus height of the effect times 0.5 in this random range. This will separate them out and prevent them from making groups. I also have to copy this and use the same code here for the initial page load. Particles and the lines connecting them disappear instantly when the reset happens. I want to make sure we only reset when particle and the line connecting it to another particle is fully outside the screen, and only then we will reset. I turn this into a class property to make maximum connection distance available all over my codebase, not just inside connectParticles method. I turn it into this.maxDistance property on the main effect object. I set it to 100. I have to use this dot here and here. I reload. Yes, it still works. I only want to reset the particle if the entire particle and the line that is potentially connecting it to another particle would be completely hidden off screen. This covers the bottom edge. I will also reset particles that move off screen to the left, so minus radius minus max distance, and also to the right when horizontal x-coordinate is more than effect width plus radius plus max distance. So if particles are off-screen to the left, right or bottom, and they are far enough that the entire particle and the line connecting it is hidden, we reset them back to the top so they can fall again. I want to include max distance in the reset position as well here, and I copy that. And I use it here. It takes a while before they start coming, but they eventually do. What about height times 0.2 here and here? I want particles to collide with text. Let's start by drawing their hitboxes. I will create a property called debug. Initially, I set it to true. I create an event listener for keydown event. When we press letter D on the keyboard, we will toggle debug mode on and off. We set this.debug to its opposite. If it's currently true, set it to false. If it's false, set it to true. I want to create a reference to the h1 heading element in my code. I will save it as this.element property on effect class, and I point the JavaScript towards it using getElementById. I gave it an ID of caption. Once we have it, I will call built-in getBoundingClient rectangle method, which returns an auto-generated DOM-rect object, providing information about the size of an element and its position. I'm running this code locally, but we should probably run this code inside a load event listener, especially if the HTML element is a big image. I'll do that later. We need to make sure that this JavaScript runs only when the entire web page is fully loaded and the element is actually there. We can see the element's x and y position, width and height, and other measurements. It measures the smallest rectangle that contains the entire element, including its padding and border. These properties are relative to the top left corner of the viewport. So if this.debug property is true, we stroke rectangle from element x, element y, to element width, and element height. Now we can see the bounding box. I want particles to bounce off that rectangular bounding box, so let's draw their collision areas as well. Particles are circles, bounding box is a rectangle. In this case, because particles will bounce when the bottom of the particle hits the top border on the text, we can actually use collision detection formula between two rectangles, and we will consider particles as if they were rectangles, even though they are circles. Let me show you what I mean. For this particular effect, it will make no difference. I say, if this.debug is true, because I want to draw collision boxes only in debug mode, we will stroke rectangle, the collision hitbox around each particle. I want to draw it from particle x and y position, and width and height will be radius of particle circle. They take a while to appear on the screen, so on the first page load I adjust their vertical position. We have here maybe times 0.5. We know that radius is only half of a circle, so if I want width and height of the rectangle to contain the entire particle circle, we will need to use radius times 2, here and here. X and Y coordinates on canvas define the middle, the center point of a circle, but with rectangles they define their top left corner, so I have to offset horizontal X position by radius to align the hitboxes over particles horizontally. And I do the same for vertical alignment. We see hitboxes on the big text that says welcome, and we also see individual hitboxes of each particle. How do we make them bounce now? We are going to use the standard collision detection formula between two rectangles, but because we are offsetting particle rectangles to align over circles, we are making it a little bit more challenging for ourselves. Drawing these rectangles over particles on line 31 will help us to see it easier, because basically this entire thing is x coordinate of particle rectangle now. This entire thing is the vertical y coordinate, this is width, and this is height. I need to use these values in collision detection formula. Let's quickly do it step by step, I will show you what I mean. You can find many articles online about 2D collision detection. Rectangle versus rectangle collision is by far the simplest one. They give us the formula here, so I copy this code block. Don't worry, I will give you enough time to type this and go over it with me. I just paste it here. In this case, rectangle 1 will be particle. Rectangle 2 will be the hitbox around the welcome sign or any other HTML element you might be using. This would also work with multiple elements. The formula says only if all 4 of these checks are true, collision is detected. If at least one of these checks is false, we know the two rectangles can't collide. There is no collision. You can only collide if horizontal position of rectangle 1 is less than horizontal position of rectangle 2 plus its width. If this is to the left of this. Also, at the same time, only if horizontal position of rectangle 1 plus its width is more than horizontal position of rectangle 2, if this is to the right of this. If both are true, we know they collide horizontally, but they could still be far away from each other vertically. That's why we have to do these same checks, but this time for the vertical axis. If vertical position of rectangle 1 is less than vertical position of rectangle 2 plus its height, if this is above this. And one last check, if vertical position of rectangle 1 plus its height is more than vertical position of rectangle 2, if this is below this. Only when all 4 of these checks are true, collision is happening. If at least one of these 4 checks is false, the entire expression will evaluate as false, and we know there is no collision. Rectangle 2 is a hitbox around the welcome sign text. It's just a simple rectangle, and I can replace rect2 in all these 6 places with this.effect.element. Element is auto-generated DOM rectangle object. We know it has x and y properties, but I notice its width and height are spelled differently than in my formula. I have to say width here and height here. Now it will work. Rectangle 1 is the white collision rectangle that we aligned over each circular particle object. We are inside update method on particle class, so to refer to each particle from here, I will use this keyword. Because circles and rectangles are drawn differently, x and y of a circle is the middle of the circle, and x and y of a rectangle is the top left corner of the rectangle. I had to adjust these values here to correctly draw hitboxes over particles. So for collision detection purposes, we don't care about the particle circle. We care about the rectangle that was offset to contain that particle and that travels with it as the particle moves. This entire expression is x-coordinate of that rectangle, so I copy it and I use it as the x-coordinate of rectangle 1, of particle rectangle, in collision detection formula. I do that here and here. This entire expression is the width. I actually don't want to be calculating radius times 2 for every particle 60 times per second. To save ourselves a little bit of performance, we will pre-calculate that value just once when the particle is created, and then we will use that pre-calculated value. Width and height of the particle is radius times 2. Now I can use this dot width here and this dot height here. I can delete this. Actually, let's use colors just for debug purposes. This dot color will be white. We will set stroke style to this dot color here. If collision is detected, this dot color will turn red. Otherwise, if no collision, it goes blue to get a better contrast. I can even fill those rectangles to see it more clearly. I want the bouncing area to be just the slim border that sits on the top of welcome text, so I don't need the entire height of the element. I can just do 5 pixels. Note from the future, we are offsetting this.x by radius here and here. At this point, I didn't do it for this.y here and here. These values should also be offset by radius. It's not noticeable at this point, but it will become more obvious in a second. If you noticed that, don't worry, I will fix it soon. I remove all references to this dot color. It was just a test. We know that particle rectangles are detecting when they touch and when they are inside the big element rectangle. If collision is detected, I will simply flip Vy, velocity y, to its opposite value. And we get this. This is the main logic of the effect. If you want to make it fully responsive, polish the effect, fix a few small bugs and experiment with it. I'll see you in the next part. How to combine particle systems with other HTML elements on the website and make them interact together. Let's draw particles that fall down across the screen and bounce when they hit a predefined HTML element. Check out the video description for a link to part 1 or to the full Particle Systems Masterclass playlist. Today I will finish this project by showing you how to make it fully responsive, how to make it work even when Canvas doesn't cover the full browser window, and then we will play with the code and experiment with different visuals. Have fun! When I resized the browser window, the collision area is no longer correctly covering the HTML element. I have to copy line 72, where we use getBoundingClientRectangle method to measure element size and position, and I have to call it again from inside our custom resize event to get its new X and Y position after the window changes size. Now, when I make the browser window larger, the collision box always correctly covers the element. That was easy. On line 52, we can change the power of the bounce. Let's say I want particles to only have half the energy after they bounce. You can see that sometimes particles kinda stick to the element. They are not bouncing correctly. It's because they get stuck inside it. Remember how I had to offset X and Y position of rectangles to correctly place them over circular particles? I am offsetting X like that here, and I forgot to also offset Y here and here, because when it comes to collision in this project, we care about the rectangular hitboxes that travel with particles. We don't really care about the circular particles themselves. Now that we fixed the formula, I will create a hard stop to make sure particles can't fall too far from the element, making them stuck. Let's see. That's better. Particles slowly lose bouncing energy because of the code we wrote here. So what if I want them to bounce a specific number of times, and if by that time they still haven't fallen off the edges on either side, I will allow them to fall through the element so they can reset and continue the cycle. I create a property called bounced, and I set it to 0. I let them bounce 2 times, and then I will allow them to fall through by including this check in the collision formula. Every time they bounce, I increase bounced by 1. And when they reset, bounced has to be reset back to 0. You can change the number here to allow them to bounce more times before allowing them to ignore the collision area and continue on their way. I resize my text and I reload my project to measure the element again. I don't like how a lot of particles sit for too long in this area barely moving. I can give particles more horizontal motion by setting Vx to a random value between -1 and +1. Every time they bounce, I will increase their vertical movement by 50%, further pushing them to one side, increasing the chance they will fall off the edge. Colliding with the text now gives them horizontal movement boost. It's just one of the options we can do. I will let you to decide what looks better. Since we are manipulating Vx, we need to make sure it always resets back to its original default value, so I copy this line and I paste it here inside particle reset method. Otherwise, these increases from line 57 would persist between particle resets. Okay, that's one thing we can do. Keep in mind that all this will run math.random quite often in our code, and running math.random too much will affect performance. Another movement option would be this. I delete this line. I really like when they create kind of a sideways stream. Let me show you what I mean. I set the initial X position to the left edge of the element. I want them to start falling from here. When I use this.effect.element.x here, I get a console error. It's important to understand why we are getting this error. It will help you with debugging not only for this project, but for many other object-oriented code bases. It's all about the sequence in which all our code is being executed and when the particles are being created. I'm using my particle class to create 300 particle objects here on line 75, and only after that I'm creating the element. That's why at this point, when I'm triggering particle class constructor, reference to this.element doesn't exist yet in our code. This line hasn't been executed yet. I cut all this code and I put it after I created the element, and now they finally start coming from the correct position. I set Vx to a random value between 0 and -2 to make them move to the left. And I want the initial X position to be the right edge of the element here. So element's X position plus its width. Nice. Maybe even a bit further to the right. So width times 1.5. I copy this line of code and I need to make sure I use the same code inside particle reset method. This is pretty nice. If you are getting FPS spikes and performance issues, you can reduce the number of particles. We are doing quite a lot of calculations per second here with collisions and lines between particles that have dynamic opacity. There is actually a lot happening here. Well done if you are a beginner and you managed to build this with me. I copy Vx and I put it inside the reset method again. We will need it for later. So this is what we have so far. It's fully responsive and we understand the code well enough to tweak it and to control the particles to make them fall in any direction and from any point we want. Let's play with the drawing code now. This is a really cool trick you can use for any animated canvas effect. What is an easy way to give particles trails? We are deleting canvas paint between every animation frame. What if I disable that code on line 165 and instead I will draw a semi-transparent rectangle over my canvas, not completely deleting the old paint, just covering it slowly step by step by a barely visible rectangle. This will only work for effects when you don't need canvas to have transparent background. I set fill style to 000 black with 0.2 opacity. This will disable our gradient fill, so up here. This needs to be let instead of const. Gradient will be from white to magenta to pink, for example. Then I copy all this, but without let keyword. I want to reassign to the same variable, not to redeclare it like we are doing now. And I paste that here. Notice there is no const or let on line 151. I'm reassigning here. And I need to set fill style somewhere, ideally here inside handle particles, so we do it once for all 300 particles rather than declaring fill style for each particle individually inside their associated draw method. If I was to be thorough here, that gradient code maybe would be better sat on my main effect object. Technically, I am now pulling a global variable, gradient, from outside my class. It's always better to keep our classes as self-contained as possible. Particles have trails, and I can make the trails shorter or longer by adjusting the opacity, here on line 167. Now everything on canvas is kind of smudged. We see old paint disappear very slowly, step by step, creating this cool effect. What if you want particles to leave trails like this, but the lines connecting them to be sharp? We could do that by drawing particles on one canvas element and the lines on another canvas with different clear settings. It's a very common thing to do. You can try it or keep following the series. One of the effects I will show you will use multiple canvas elements to do something very cool. Max distance property should actually sit on the effect class. I cut it and I paste it here. That's better. The effect will work when you resize the browser window. The problem is that it will only work if canvas is full screen, if canvas is the same size as the browser window. What if I want to make it even better and make it work for any canvas size? I set canvas width to 700 and canvas height to 800. Maybe 600 times 800? Make sure you are not setting canvas size with CSS, because that would be setting only the element size. If you set canvas using these two declarations, you are setting both canvas element size and drawing surface size at the same time, which is what we need to do here. I center canvas in the middle of the web page with CSS like this. Particles won't even come at all. I can make them start falling by setting X to the middle of the page, like this. I can also make them fall to both sides by adjusting Vx value. If I press D on my keyboard to enable or disable debug mode, I can see that the collision area of the text is now off. It is misplaced exactly by the edge between canvas and the web page here and here. That's a problem and it breaks the entire effect. I can fix that by using the same techniques we already learned. Same as I am measuring the element to get its XY width and height using getBoundInclinedRectangle method, I will also measure canvas. This.canvas size is this.canvas from line 70, which already references the canvas element from before,
and we measure it by calling getBoundingClientRectangle on it again. If I open the console, I can see the auto-generated DOM-rect object showing me x, y, width and height of canvas in relation to the viewport. This is exactly what I need. How do I write the code now? I guess to keep it clean, I can, for example, create another property called heading, representing the HTML h1 element that says welcome, and in there we will pre-calculate its correct x, y, width and height. X will be element x minus canvas x to account for that potential space between the web page, edge of canvas, and where the element actually starts. I will also account for the potential space between canvas and the page vertically. Width and height will be just width and height of the element, it stays the same. So now, this .heading represents the accurate measurements of the element. So I will replace all references to this .element in the collision detection formula with this .heading. I also need to do it in all these places. Now it works. But still, when I press D, I want the collision box to be correctly drawn over the heading, so I replace element with heading here on line 131. When I resize, it breaks. So I have to copy all this code. And I also have to put it inside custom resize method here as well. Now the collision box sticks to the text when we resize, and it registers collision correctly even when I resize the canvas. Even when canvas is not full screen, when canvas is, for example, 800 times 500 pixels, because we are accounting for the edges between canvas and the page. Everything still works perfect. I set width and height back to what it was before, here and here. And I make canvas full screen again, because we know it works when it's not full screen now. What if I want the particles to start falling from this range, exactly above the heading? Between heading X and its width. As usual, I have to copy this, and I have to put the same code inside the reset method. Nice! We allow particles to bounce a few times and then they fall through. I also have to adjust Vx here on line 63. They bounce 5 times and then they fall through the element, ignoring the collision area. I can give them horizontal speed boost again every time they bounce, making it more likely they fall off the edge. I think this looks better. I only reduce the energy to 60% here. I boost horizontal speed times 2 every time they bounce. I can also increase the number of bounces to 10. This will result in particles sometimes shooting really fast to the sides when they bounce many times, each time increasing their Vx times 2. I think it's fine. I really like what it looks like now. Since we are measuring position of elements on a web page with JavaScript, we only want JavaScript code to run when the full web page and all its elements are fully loaded. One way to do that is to wrap all this code inside a load event listener. JavaScript runs very fast. We need to make sure that the HTML element is created first and JavaScript runs after, especially if you choose your HTML element to be something that takes a bit longer to load, like an img image tag, for example. I showed you how to tweak this, so feel free to run your own experiments. This is creative coding. There is no right or wrong settings. How to combine particle systems with custom graphics and make them interact together. Let's draw particles as star constellations, make them scroll across the screen, and add an animated creature that the particles interact with. Let's explore some of the most fundamental techniques and then put them together as more unconventional combinations. This is a bonus experimental section of Particle Systems Masterclass. You can download the base source code from part 1 in the resources section below and code with me today, or if you want to understand every line of code, watch me write it and explain it from scratch. The full playlist is linked below. Click the like if you want me to do more of these and leave a comment with your ideas and thoughts on unique particle effects.
Right now our particles are simple circles. What if I want to use an image of a star to represent each particle object instead? It's very simple, and drawing and animating images on canvas is often more performance efficient than drawing shapes with code. There are many ways we can bring an image into our project. The simplest way would be to include it in index.html like this. You can download all project images in the resources section below. I placed the image inside my project folder. I called it star.png. And I gave it an ID of star. I don't want to draw the image element itself on my web page, so I hide it with CSS. I just want the image to load in memory, and I will draw it with JavaScript on canvas. This is a local project, so I will just bring the image in. If you want to put this code somewhere online, you need to wrap all the JavaScript code inside event listener for load event. Or you could also add onload event to body tag. I will show you how to do that at the end. For now, we are working locally, which means the image will be loaded instantly. We don't have to wait for it, and I can just bring it inside my JavaScript project as this.image property on particle class. I point it towards that image using the ID I gave it. Whatever code we put in here, that's what each particle will look like. Right now, we are just drawing a circle representing each particle. I can use built-in drawImage method. It expects at least 3 arguments, the image we want to draw, and x and y coordinates where to draw it. I change the radius to a random value between 1 and 7 pixels. Right now, all star images are being drawn at the actual size of the image. I can pass drawImage method optional 4th and 5th arguments to define width and height, but that will make them very small. Let's make it a multiple of radius, maybe radius times 8 for width and the same for height. Now we have stars of randomized sizes. It's not very performance efficient to calculate radius times 8 over and over for every animation frame for each particle object. What if I pre-calculate that value just once when we create the particle and then we use that? I will call it image size and it will be radius times 8. Then I use it for width and for height. Nice! Circles on canvas are drawn around a center point. Images and rectangles on canvas are drawn from the top left corner, going right and down. To align the rectangular images over circular stars, I offset their horizontal position by half of image size, and I do the same vertically. We don't need this code that draws circles anymore, but we still need the images to be aligned and centered over x and y coordinates to make our physics and push forces act on the center point of our stars. Again, instead of calculating values here for every animation frame, I can pre-calculate that in a constructor. Half image size is image size times 0.5, and we replace it here and here. We have an interactive star system. This looks nice. What if I want to create an illusion that we are flying through space and the stars pass us by? I set Vx to -1 to make them all flow to the left. I will remove Vy, we don't need it for this effect. I also need to remove Vy here. The stars are bouncing because of the code here. I will actually need only one of those checks. I want to check if stars moved past the left edge of canvas, and if they did, I want to reset them behind the right edge so that they can flow over the screen again. If x is less than radius here, set x to effect width here. If you build any games with me, I'm sure you realize how this can be used as a cool interactive background for a side-scroller game, for example. The stars just disappear instantly and they reappear here. I want to mask that transition to make it look more natural. The stars are also connected by lines, so I only want to reset them when the star image itself and the line that is potentially connecting it to another star is completely hidden off screen before I make it disappear and reset. That connection distance between stars is defined here. so I turn it into a property on the main effect class to make this value available all over my code base. I have to use this dot here and here. And now I can access max distance property from inside particle class. If particle's horizontal x position is less than minus image size minus this.effect.max distance, only when the entire particle and the line connecting it is completely off screen to the left, only then reset it behind the right edge again, accounting for that image size and for maximum connection distance. We get a gap in between now, which becomes more obvious if I increase max distance. To make it seamless, we need to adjust starting x and y coordinates of our particles. I replace radius with image size. I want the initial horizontal position to be spread slightly further to the right to fill that gap, so I add max distance. Max distance times 2 should do it. I will test it a bit further. I can do max distance times 4, but maybe that's not necessary. I will check that in a bit. Our effect is supposed to be fully responsive, so we need to keep that in mind and make sure we make all these important changes inside our custom reset method. I copy these new x and y starting coordinates and I replace them here. Now, when I resize, the effect works. I set max distance to 110 pixels. I don't need this gradient code for this effect, so let's delete it. If I push particles off screen vertically, they will be scrolling, but off screen. We are only resetting particles' horizontal position here. I also needed this line of code to run here, to make sure they return back to the visible canvas area vertically next time they reset, just in case they were pushed off screen by mouse or any other force. If this was my final effect, I would add some randomization here to make sure we don't get a static cluster that just scrolls by over and over, but since we will have a creature constantly disturbing these particles as it swims by, I don't need to do that. Let's take image I called whale1 and bring it into the project. All images can be downloaded in the resources section below. You can also use these animated whales in your games if you want. It's a free gift to the students of this course. The art style is compatible with some of my other games, so you can even mix and match. So here we have the particle class. Here is our main effect class. I will create a third class called whale to manage our intergalactic space creature. I have multiple designs ready for you. As you can see, I designed it as a living machine with solar panels for fins. The art style is compatible with my latest space game class, so if you're following that, you can use that whale in there as well. Constructor will expect effect as an argument, and we convert it to a class property pointing to the space in memory where our main effect object is stored, so that we have access to all properties and methods on the main effect class from inside the whale class. We take advantage of that immediately, and we set horizontal x coordinate to effect width value coming from here times 0.5 to put the whale in the middle horizontally. This.y will be effect height times 0.5, the middle of the canvas vertically. This.image will point to that new image we just added in index.html. I gave it an ID of whale1. I give it a custom draw method. It will expect context to specify which canvas we want to draw on and also to make sure our classes are self-contained and independent from where they sit in the code base. I call built-in draw image method. We used it already to draw the stars, so we know it expects at least 3 arguments: the image we want to draw and x and y coordinates where to draw it. We have our new whale class. Let's create an instance of it here and set that instance as this.whale property on the main effect class. It expects effect, so I pass it this keyword here. I need to call it from somewhere to draw it 60 times per second as part of the animation loop. I can do that here inside handleParticles method. I take this.whale property from line 75 that holds an instance of whale class, and I call draw method we defined. Up here on line 60. I can see it expects context as an argument, so I pass this context along. Nice, we are drawing our space whale as a static image. Because we are drawing everything on a single canvas element, and because I draw whale first and particles after for every animation frame, the whale is drawn behind the particles. If I take this line and I put it here after the particles, the whale will be drawn in front of them. This.x and this.y coordinates are exactly in the middle of the screen. But as we said before, with images and rectangles on canvas, x and y coordinates don't define the center point, they define top left corner. If I want my whale to be in the middle of canvas, I have to offset the x coordinate by a half of image width and y coordinate by a half of image height. I can position it slightly off to the left like this. We want this effect to be fully responsive, so I have to make sure these position values are recalculated when width and height of the effect changes. I can delete all this code, and instead I set x to new width times 0.4 and y to the new height times 0.5. Now, when I resize my browser window, our custom resize method fires and the whale stays centered. Nice, we have a creature floating in space. There are so many things we can do with this now. Let me show you something. How to combine particle systems with custom graphics and make them interact together. Today we learn about rotation, motion patterns and sprite animation. The full playlist is linked below. Let's go! I want to make the whale sway up and down as it swims. I give it this.angle property. Initially, I set it to 0. VA, velocity of angle, will determine by how much will the angle increase per animation frame. I give it an update method. Inside, I will increase angle by VA. So, we have an ever-increasing angle value that increases by 0.01 every time update method runs. For most of us, that's 60 times per second. Now I want to update vertical position of the whale. I want it to sway up and down around the middle of canvas, so this.effect.height times 0.5, and then we add a sine wave, math.sine, and I pass it that angle value. When you pass an ever-increasing angle value to math.sine, as the angle increases, this method will map those values along a sine wave shape, like this. I will call this new update method from inside handleParticles to make sure it runs 60 times per second. By default, the sine wave will go between -1 and +1, very small value range, so we can't really see it. I need to increase the radius of the wave by multiplying that value. Now we can see some movement. As we increase this.angle value, math.sine is automatically mapping that ever-increasing value on the sine wave, and we are magnifying that range by multiplying it by some larger value. I can make it relative to canvas height, I guess. Or I can create a separate property I call curve, and then use that here. I also have to make sure that this value gets recalculated every time canvas changes size. All the effects in this series need to be fully responsive, like this. If you console log this.angle, you will see it increases endlessly. It would have to run for a very long time before the value becomes large enough to actually cause any noticeable performance issues, but still, to keep our code clean, let's say I don't want to have an ever-increasing value in my code. I want to periodically reset it back to 0. But when? I say, if this.angle is more than 1, set it back to 0. You can see that doing this resets whale position rapidly when it's mid-motion. We don't want that. we have to understand that math.sin is taking this angle value in radians, and we know that half circle is equal to math.pi, approximately 3.14 radians. If we reset every time angle reaches math.pi, we get only half the motion, and then it resets and it goes again. To get the full curve that goes into positive and negative values, I have to reset after math.pi times 2. We reset now. That wasn't even noticeable. It looks like a continuous motion loop because we are resetting at the point when the whale is back at the starting position. Again, we reset now. Perfect. We are resetting angle value. It's not increasing endlessly and we still get uninterrupted motion. What if I also want to rotate my whale up and down as it moves to make sure its nose is pointing towards where it's going? This is a very easy thing to do if you understand how canvas rotation works. I'm going to assume you don't understand it and that you don't know why, when I pass angle to rotate, this mess starts happening. Rotation on canvas works completely different than rotation with CSS. Let me explain. First of all, we are rotating the entire canvas element, everything that is drawn on canvas, including the whale and all the particle stars. This shows really well how rotate method is additive. It just adds up when we call it over and over again for each animation frame. To restrict any changes to canvas state to a specific set of draw calls, I will wrap this part of code in save and restore built-in methods. Doing that will make sure that this rotate call only affects this draw image and nothing else. I want the stars to remain unaffected. Now we can see that the whale is being rotated around the top left corner of canvas, around coordinates 0, 0. Think about this point as the default rotation center point. When I want the whale to rotate around its own center, around its current x and y coordinates, I have to set those as the rotation center point by passing them to built-in canvas translate method. So here I am setting this.x and this.y, the current position of the whale, as rotation center point, and everything drawn after that will consider this.x and this.y as if it was coordinates 0, 0 on canvas for all intents and purposes. For that reason, I have to remove them from here. We don't want to double them. Position of the whale is already defined while translating here. This is the confusing part, so bear with me. We will get this to work and then we will recap how it works step by step. I will comment out the sine wave motion for a moment. Now the whale is rotating around its own center point. I want to turn rotating motion into repeating back and forth motion so I can actually pass rotate sine of the angle. This is what it does. I am basically passing rotate method a series of values that gradually cycle between -1 and +1 because of the ability of sine method to convert an ever-increasing range of values into a repeating range that cycles between -1 and +1. I uncomment vertical movement code and we get this. I'm sure this would work for some effects, but it doesn't look like the whale is swimming, is it? Lucky for us, this is a super easy fix. I just put cosine here instead. The relationship between sine and cosine will work perfectly for this. Notice we are passing sine and cosine the same increasing angle value. I could just turn this into a Flappy Bird game now. If I use both cosine, this happens. Or I swap sine and cosine. Alright, we need cosine here and sine here for this particular project. So, two things to remember. If you pass sine or cosine an angle value that slowly increases, these methods will map this ever-increasing set of numbers on a wave, endlessly cycling between -1 and +1. If you want this wave for movement, attach it to position of your object and maybe multiply it by some larger radius, because range between -1 and +1 in terms of pixels would be barely noticeable. The second thing we learned is that canvas rotate method rotates around coordinates 0, 0 on canvas under any circumstances. 0, 0 is always the rotation center point, so if you want to rotate your object around its own center point, first you have to translate coordinates 0, 0
the rotation center point over that object, and then you call rotate, and then we draw that object at coordinates 0, 0, because the position of that object becomes defined by translate. It's a lot to take in, but don't worry too much. If you keep coding with me, it will become easy. This is a very common technique, and repetition leads to mastery. For now, I want to focus on more fun aspects of this project. Let's bring our intergalactic space whale to life. Let's replace the static image with a sprite sheet and learn an easy way how to animate it. In the resources section below, you can download image I called whale2. I bring it into the project here. ID is whale2. And we set this.image on whale class to whale2 like this. This is a different type of whale. It doesn't have a flame propeller for a tail like a spaceship. I made multiple different versions for you. DrawImage method expects 3, 5 or 9 arguments depending on how much control we want over the image we are drawing. Right now we are passing it just 3 arguments, the image we want to draw and x and y coordinates where to draw it. We are also offsetting it by a half of width and a half of height, so we are looking at the middle of this long, wide sprite sheet. Sprite sheet is a single image file that contains a set of individual frames. We can animate it by cropping just a portion of the image, and as we travel over the sprite sheet, cropping out different parts, we get animation. To effectively navigate around the sprite sheet, cropping out frame by frame and create animation, we need to know the width and height of individual animation frame in that particular sprite sheet. I created this sprite sheet for you so I know that sprite width, the width of a single frame, is 420 pixels. We can also calculate sprite width by taking the width of the entire image and dividing it by the number of columns, the number of frames per row. Sprite height is 285 pixels in this case. So let's pass DrawImage optional 4th and 5th arguments for width and height. And I want to draw it at coordinates 0, 0 because we are translating to this.x, this.y here on line 67. So this is the second version of DrawImage method with 5 arguments. We can stretch the image like this by passing it different width and height values. Right now, we are squeezing all 38 frames of the sprite sheet into an area of 1 frame. For clarity, I will comment out this line and this line as well temporarily, just so we can clearly see what's happening. So we are translating coordinates 0, 0 from the top left corner to this.x, this.y of the whale. We do that to make the rotation work. Then, from those translated 0, 0 coordinates, we are defining width and height of the entire sprite sheet to be 420 times 285 pixels. To animate a sprite sheet, we need to use the longest version of DrawImage method that accepts 9 arguments. This version gives us the most control over the image we are drawing, and it's important to understand it if you want to animate sprite sheets or if you want to build 2D games. We need to pass it 9 arguments, the image we want to draw, source x, source y, source width and source height of the area we want to crop out from the source image, and destination x, destination y, destination width and destination height to define where on destination canvas we want to place that cropped out piece of image onto. So first, let's just crop out the left frame, so cropping area will go from coordinates 0, 0 on the sprite sheet to sprite width and sprite height. Okay, we are cropping out this frame and we are drawing just that frame on canvas. Again, if I want to center it, I need to offset destination x and destination y arguments by a half of sprite width and a half of sprite height. We can now animate it by jumping through the sprite sheet frame by frame. We will do that using a helper variable I call, for example, frame x. Initially, I set it to 0. I will also need to define max frame. When frame x reaches max frame, it will reset back to 0 so that it can cycle through all those frames again. Source x argument allows us to navigate around the sprite sheet horizontally. By pushing the starting x and y position of the cropping area around, we define which area, which frame is being cropped out. I do it like this. 0 times sprite width is 0, so that will crop out the left frame. 10 times sprite width will move the cropping position here, and now we are cropping the 10th frame. So let's make this dynamic and replace this value with our helper frameX variable. We know that as this number increases, we are cropping out different area of the sprite sheet. So when frameX is 0, we are cropping this frame. When it's 1, we are cropping this frame, 2, 3, 4, and so on. Now I just need to make sure that frameX endlessly cycles between 0 and max frame. Here I'm using a ternary operator. I'm using it as a simple one-line if-else statement. If frameX is less than max frame, increase frameX by 1. Else, meaning it's more or equal to max frame, set frameX back to 0. And we are animating. So ternary operator used as a simple one-line if-else statement. Expression to evaluate, question mark, if true, do this, colon, else, do that. This is how you animate sprite sheets in JavaScript without using frameworks or libraries. It's a very common and useful technique. I use it in many different projects. I uncomment the up and down motion, and I will also uncomment rotation. Notice that we are increasing frameX by 1 for every animation frame here. This means that the frames will cycle at the maximum speed. Because we are controlling animation using built-in request animation frame, this means that animation speed automatically adjusts to screen refresh rate. For most of us, that's 60 frames per second. On high refresh rate gaming screens, it will be much faster, and this animation probably moves too fast for you. What if I want to get more control over the animation and I want to make sure each frame stays on the screen for a set amount of milliseconds, meaning that the sprite sheet will animate at the same or similar speed on all different machines? How to manually control FPS and how to use milliseconds to time and trigger periodic events, such as serving another animation frame every 16 milliseconds, for example? We can easily do that with timestamps and delta time. How to combine particle systems with custom graphics and make them interact together. Today we'll learn how to time animations in milliseconds and how to trigger periodic events. The full playlist is linked below. Let's go. Again, this technique is very common and extremely useful. First, I need a variable here that will keep track of timestamp from the previous animation frame. I will call it last time. For every animation frame, we will calculate delta time. Delta time is the number of milliseconds it takes our computer to draw one animation frame. It's the difference between the timestamp from this animation frame minus the timestamp from the previous animation frame. Where is this timestamp value coming from? It is being automatically generated by request animation frame method, and it's being passed to animate as an argument. It's invisible, but imagine it's being generated and passed here, like this. It's one of the special built-in features of request animation frame method. To use that timestamp, all we have to do is give it a variable name here, and the JavaScript will automatically know what we want. Once we used last time to calculate delta time, we assign it to the timestamp from this animation frame, so that it can be used again in the next animation loop. Timestamp is only generated for the second animation loop that gets initiated by request animation frame. The first call of animate comes from here, and there is no timestamp being automatically generated. If timestamp is undefined, delta time would be none, not a number for the first loop, because of this calculation. So I avoid that problem by passing timestamp 0 just for the first loop. All other loops will have actual auto-generated timestamps, because after that initial call, we are calling animate through request animation frame on line 175. So for every animation frame, request animation frame method is auto-generating a timestamp value, which simply gives us the number of milliseconds since the first loop started. We are giving it a variable name timestamp, and we are using it to calculate delta time, the difference in milliseconds between the timestamp from this animation loop and the timestamp from the previous animation loop. When we used last time to calculate delta time, we assign it to the current timestamp so that it can be used again as the old timestamp in the next animation loop. As the animation runs, we are comparing the current and the previous timestamp, and we are getting delta time. I pass that delta time to handle particles method. To check if the calculation works, let's just quickly console log it. I can see my delta time is 16.6. 1000 milliseconds divided by 60 is approximately 16.6, so I know my computer is serving around 60 animation frames per second. Each frame stays for around 16 milliseconds before it gets updated and replaced. Let me know if you're getting the same number. If you have a high refresh rate screen, you will get a lower value on delta time, because your computer can serve more frames per second. On those fast screens, the whale is also flapping around very fast, probably, so let's unify that animation speed for all machines. I know how many milliseconds pass between frames, so now I can use that value to trigger periodic events. For example, I can say something like, only update sprite frame in the sprite sheet every 50 milliseconds. Doing this will make sure that the whale animates at the same speed on slow and on fast computers. I'm passing delta time to handle particles, so on line 125 I make sure that value is expected. From here I will pass it along to update method on whale class, and I make sure it's expected here on line 74. So now we have access to delta time from inside update method on whale class. To use this value to trigger periodic events, we need two helper variables. Timer that will count between 0 and a specified interval value. Every time it reaches that interval, it will trigger the event by running some code, and the timer will reset back to 0 so that it can count again for the next event. The interval will be, for example, 1000 milliseconds, 1 second, divided by 50. I want to update cropping area in the sprite sheet 50 times per second. We will handle that FPS here. I say if frame timer is more than frame interval, do something, else do something else. If it's more, run all this sprite animation code to increase frame X value and also reset timer back to 0 so that it can count again towards the next periodically triggered update. Else, meaning the timer is not yet more than interval, keep increasing timer by delta time. And that's it. This is how you control FPS of a specific object. The same technique can be used to control FPS of the entire animation project if used in the main effect class, and we can also use this to trigger other periodic events. For example, I want a random planet to float by every 5 seconds, or I want the whale to blink every 3 seconds, things like that. Now you know a technique how to time any regularly repeating events in your project. When the timer is more than frame interval, we are resetting timer back to 0. There will usually be some leftover milliseconds that we are just discarding and we are not accounting for them anywhere. This will help with performance because we are not doing these extra calculations, but it also means that this value that suggests we are animating 10 frames per second is actually a bit less. It's actually not exactly 10. Or not exactly 55, because we are discarding the leftover delta time rather than accounting for it. If I set this to 60 frames per second, it's actually lower than that in reality. But since we understand this, we can set these values with this in mind, or we can include that leftover delta time in our if-else statement on line 82. I prepared one more whale sprite sheet, which has 4 different whales on it. You can download it in the resources section below. The way I organized this, every row in this sprite sheet is a different whale. This will be important now. I set this.image to whale 3. This will animate the new sprite sheet, and we can now switch to a different whale by adjusting vertical cropping coordinate, source Y. 0 times sprite height is this row, blue whale with a tail. 1 times sprite height will give us this different whale design. 2 is this one, and 3 is this one. I create a helper variable, I call it this.frameY. I use that variable here, and now I want a different random whale every time I reload my page, so I set frameY to a random value between 0 and 4. I need integers because there is no row 1.5, for example. Wrapping this in math.floor means frame Y can be only 0 or 1 or 2 or 3. You can try to refresh your page now and you will get a different random whale out of these 4 every time you do that. I check if it's still responsive. Yes. When I resize the browser window, everything still works. Particles react to mouse, but for this project we want them to react to the whale instead. I can delete this block of code. We keep resize event listener, and we can delete these other 3. Right. Now we need to go up to the custom update method on particle class. This code runs only when mouse is pressed, so I remove this line and also the closing bracket. I want this code to run for every animation frame. I replace this.effect.mouse with this.effect.whale in all these places. Mouse object had a radius value to define the interaction area. Whale doesn't have it, so I go down here to my whale class and I give it this.radius property. I set it to 200, for example. Let's check. Yeah, I think that's it. I save and reload. Nice. Particles react to the whale. That was easy. How can we polish this now? I set background to linear gradient between these 2 colors. For this project, I'm going for Guardians of the Galaxy oversaturated colorful space. It's more fun like that. Let's make it larger. I want to increase the number of particles and I want to increase max distance, which means more particles will be connected. Be careful when increasing these 2 values, as both of these have a massive effect on the performance. Well done for getting this far. Our intergalactic space whale is warping space and time. Even Constellations get out of its way. Probably the best thing to do here would be to set the number of particles relative to the available screen area to make sure we have the same particle density on a small and large screen. For now, I will go with these values. I like how we have star constellations coming from the right and then they get disturbed by the whale. We can tweak the interaction by, for example, adjusting this.friction value. We can make the stars harder to push by setting friction closer to 0, or we can make them easy to push and light by setting this value close to 1. We never want to set friction to 1 or more than 1 for this effect. I can change the speed of scrolling stars here, make it slower. This.curve affects how far up and down from the middle of the screen the whale goes. Value we pass to rotate method here will determine how much it will turn as it swims. Feel free to play with these values, it should make it very clear what they do. I think 0.4 is the right value for this here. I go back to height times 0.2 here. This curve value should probably be relative to the size of the whale rather than to the size of the screen. There are so many things I can do here. I think the stars need to be scrolling past much faster. How about 1.5 pixels to the left per animation frame? I actually don't need space between stars and the top and bottom edge of canvas, so I can simplify this line of code. Also, times 2 is enough here to cover the space between particles as they reset horizontally. I need to make sure we copy this and we use the same values in reset method. I test it. Yes, resizing still works. We are using images in our project. It works for me because I'm running my code locally, so all images are loaded instantly. If I wanted to put this code online, I need to wait for images to be fully loaded and available before we run any JavaScript code that depends on those image files. The simplest way to do that is to put all our code inside a callback function on event listener for load event. I cut it and I paste it here. Like this. Do you have any other ideas on how to improve this? How about the stars slowly returned back to their original position as the whale swims past them? To achieve that, you would have to capture their initial positions. You would have to keep in mind that the initial position is scrolling to the left, and then you could say if particle's current position is not the same as their initial position, move slowly towards it, for example by 1/10 of the distance. It's a challenge for you. Can you implement it?
In this project, I want to explore more advanced physics where particles are spatially aware of each other and interact as if they were solid objects. We will use multiple canvas layers and liquid filters on top of that to make it even more interesting. As always, we start from the basic code base. You will have this code if you followed the first set of lessons, or you can download it in the description down below. I will set canvas background to linear gradient, but I want to give it sharp transitions. So let's start yellow to black. Yellow will go from 0 to 25%. Red will go from 25% to 50. Blue will go from 50 to 75. And black will go from 75 to 100%, like this. I will set canvas position and I will use a filter property. I will blur canvas element and everything we are drawing on it. When I blur like this, we can see the white body of the web page around the edges. For this effect, I would prefer the edges to be dark, so I set background on the body element to black. For the liquid effect, we first blur the canvas and the particles drawn on it, and then we sharpen the blurred edges with contrast, like this. Particles and lines we are drawing on canvas are too small and too thin, so the filter makes them disappear completely. We can still see how they disturb the boundaries between gradient colors as they move around. Interesting. If I want the particles to be this small and remain visible, I have to draw them on a separate canvas. On a canvas that doesn't have the blur filter applied. I create another canvas element with an ID of canvas2. Here I define some CSS values shared for all canvas elements in our project, and only canvas1 will have gradient and filter applied to it. Now I can bring that second canvas into the project by copying these 4 lines and adjusting them. If I want something to be drawn on canvas 2, I just use this new ctx2 variable now. Handle particles will expect context2 as the second argument, and lines connecting the particles and also the particles themselves will be drawn on canvas 2. Here we call handle particles, we pass it ctx and ctx2. We are seeing old paint. I need to make sure I clear canvas 2 between every animation frame. Now we are drawing gradient on canvas 1 and particles on canvas 2. It means we lost the color interactions between the particles and the gradient when the particles cross the boundaries between gradient colors. I liked that interaction and I want to keep it, so I will actually draw particles on both canvas elements at the same time. Particles are sharp and fully visible, and at the same time they disturb the boundaries of the gradient as they move across. I like this effect. I can point this gradient to go directly from top to bottom and go from black to white. I could also create a sharp boundary in that gradient, like this. And I can also apply it to stroke style to draw the lines with these colors. We get an interesting effect. For the next step, I will make the particles larger. Radius between 5 and 35 pixels. I will reduce the number of particles to 100. Here, where I create the particles, we have this index value, which goes from 0 to 100. I will pass this index to each particle as we create them one by one. I want each particle to have a unique index property. Up here, I make sure that value is expected and I save it as this.index property. I can say if this.index is divisible by 20 with a remainder of 0, make the particle larger. Radius between 50 and 70 pixels, for example. Otherwise, make smaller particles between 5 and 35 pixels. Every 20th particle will be much larger than the others. I set stroke style to white, and I uncomment this line to outline the particles. The lines connecting the particles are too thin. This area is restricted by save and restore, so if I set line width to 3 here, it will affect the lines connecting the particles, but not the particle outlines, not the stroke we are applying to particle circles. For my effect, I will now comment out the lines connecting the particles completely because I want to focus on physics between particles anyway. I will set fill style to blue. The reason we have these black shapes behind the particles is because, if you remember, I'm drawing the particles on both canvas elements, and the background canvas, canvas 1, has fill style set to black by default. So we are seeing the blurred background particles. I will give canvas 1 blue fill style and white stroke style. This looks cleaner. I will increase the friction force, making the particles move slower when we push them around with a mouse. Now the actual physics. I want the particles to be spatially aware of each other. I want each particle to always make sure it is not sitting inside or overlapping with another particle. I want them to turn into solid objects that can push each other around. So I want each particle to compare its position to every other particle and check if they overlap or if they collide. If they do, I will make them move in a direction away from each other's center point until they are not overlapping anymore. Inside update method on each particle, we will cycle over all particles inside particles array. This particle itself is in that array as well, and I don't want it to check collision between itself, so I will say only run this code if the index of the particle we are comparing is not the same as this particle. Don't compare this particle to itself. Compare it only against every other particle in the array. I will do the usual collision detection formula between two circles. dx is the distance between the center point of this particle and the particle in the array we are currently comparing against on the horizontal x-axis. dy is the same check for the vertical y-axis. The actual distance between these two center points, between 2 points in a 2D space, is a hypotenuse of this imaginary right triangle. We can get that distance by Pythagoras theorem formula, or even simpler by built-in math.hypotenuse method. I pass it dx and dy, and it will calculate the distance, the hypotenuse, for me. We will calculate sum of radii, radius of this particle plus radius of the particle we are checking against. If the distance between the two center points is less than sum of radii, we know that the particles collide. I want to push them apart, so I calculate the horizontal vector of the push, the ratio between the distance on the horizontal x-axis and the actual distance between the center points. This will give me a value between -1 and +1 that I can use to push the circles apart away from each other. Vertical vector of the push will be divided by distance, and again we know distance is hypotenuse, the longest side, so we will always be dividing a smaller number by a larger number, meaning that this value can't exceed 1. Now I will position this particle in a way to push it in a direction away from the other particle's center point, if they collide. So the position of this particle will be equal to the horizontal x position of the particle we are colliding with, plus, and here I want to push it outside the other particle's radius, so sum of radii, plus a further 0.1 pixels to make sure they are fully outside, and this check is false. And we apply a direction we calculated before, so we know how far to the left or to the right we want to push it. Vertical position of this particle is vertical position of the particle we collide with, plus push just outside its radius in the correct vertical direction, up or down. Now we have particles that see each other. They do their best to avoid overlapping. This formula can be improved in many ways, but for the basic physics, I'm happy with what we have. If you want, you can try to refactor this code and only push the particles by a small step for each animation frame, using the unit vectors we calculated. Use them to push the particles away from each other's center points in multiple steps gradually and animate that transition to get smoother effect and avoid situations where particles jump around very fast. How would you implement that? You can share your code ideas in the comments section below. There are endless other effects we can do in this series, but I think we covered a lot, and now it's your turn to play with the code, experiment, and come up with your own combinations and make your own random discoveries. Click like if you found some value. Tell me in the comments which effect was your favorite and which technique you would like to learn more about in detail. See ya!